Morning, ladies and gentlemen. So I'm kindly welcoming you on the third day of our international conference on path recognition information processing, which is online and stream, so our Telegram and VK and YouTube. And today, so we'll have an online session, and actually also we have Wednesday, which will be then we'll have offline session and closing ceremony, and also ceremony where we will see results of a hackathon during the launch hackathon touch recognition, which also will be online from streams from Changsha, National University of Defense. But now I would like to open a plenary session of this day and kindly present with applause chairman of the session, Professor, academician Sergey Blameyko, who is a academician actually and professor of Belarus State University. And so, Chairman, please, you have a floor.
Thank you very much. Good morning, ladies and gentlemen. We have plenary session, as Alexei said, and we have two presentations in this plenary session. And the first presentation, you can see here, will be given by Professor Khonchifan. Title is Object Motion Mode Identification based on radar signature. Let me say also a couple of words about Professor Khonchifan. He received the Bachelor of Science in Mechanical Engineering and Automation from Tsinghua University in 2001, and earned his PhD in Information and Communication Engineering from the National University of Defense Technology in 2008. His research focuses on information fusion, target tracking, signal processing, and intelligent guidance systems. With a strong record of contribution to both academia and applied research, Professor Fan is recognized as a leading expert in advanced guidance and control engineering. I also know personally Professor Fan, and I saw his results. It's really very strong scientist, and we are very grateful to Professor Fan to give today our speech for our conference. So please, Professor Fan, join us online. Let's look. Okay, floor for you.
Hello, Professor.
Hello, we hear you.
Hello. How you begin?
Yeah.
Colleagues, from the Regional University of Information, it's a great honor to share my research with the conference today. As we know, the object motion model reflects the current motions and the intention of the objects. Heavily and correct version of the definition is a great significance of the motion function of moving algorithm to the estimation of calculated inputs. My presentation will carry a calculated example which is the principle of motion mode based on various signatures. The main contents of the report includes the following 5 parts. First, what is user mode communication medium or method? Second, what is the communication based on user signature? Third, how to identify motion. Then, the application of motion mode inclusion of the future first approach. As it can is the first part. I want to ask you, what is the motion mode? The picture shows the human can be There are several key properties to note here. First, one target may have multiple motion modes. For example, an aircraft may fly at a constant velocity of a tuning maneuver. Second, one motion mode corresponds to one motion model, which is the foundation of our analysis of target motions through models. Third, different motion modes are distinguishable, which is important for us to conduct motion mode application. Then, let's try to answer what is motion mode application needed from the viewpoint of target tracking. During target tracking, there are two major uncertainties: motion uncertainty and measurement uncertainty, which are the key difficulties for maneuvering target tracking and multiple target tracking respectively. Motion mode identification precisely the crucial need to solving these problems. It can provide a basis for motion model selection, helping us describe target motion more accurately. At the same time, it can assist in target correlation, enabling us to better distinguish different targets in complex scenarios. Next, let's consider the case of maneuvering target tracking. From a system perspective, maneuvering target tracking can be regarded as a Markovian junction angular system, as shown in the picture. The target can switch its motion mode inside of only little sets in each adjacent instant, which make maneuvering target tracking system become a continuous, discrete hybrid system. For hybrid system estimation, motion identification is a variable rule, as shown in the bottom right figure. Timing mode identifier in practice exists in mode decision delay, which causes to motion mode mismatch of the track, increase the tracking error, even cause the divergence of the track. In our previous research, we established a motion mode decision upper under MDUE for maneuvering target tracking and inspection, which is related to the factors maneuver admissible tracking error and the mode surgeon type. As shown in this figure, the greater the target maneuvering magnitude, the smaller and a 150 millisecond motion decision delay will cause several times increase of the average distance of the cell. Let us come back to the reality. As aviation techniques advance, aerial vehicles such as modern fighter, UCV, and hypersonic vehicles have increasingly higher maneuver and speed capabilities. Thus, correct and quick motion mode decision with a small delay is urgent for this target tracking and interception. Next, we'll discuss where motion identification is based on radar simulation. As we know, compared to aerodynamics, the motion mode of aerial vehicle is directly related to its speed. Meanwhile, some radar signatures are highly sensitive to the pulse angle of a aerial vehicle, which provides a potential possibility to quickly identify motion mode with a small delay. In the following discussion, we mainly consider the signatures of aircraft body and ignore the secondary modulation signatures of its moving parts. For the latter, you can refer to the works below. As the pulse rate is a key bridge between motion mode and reader signatures. Let's start with its analysis. In the research community of reader target signature, the pulse angle is defined as the attitude angles of the inverse lag effect in the vector in the target body field, which is the phi angle shown in the figure. Taking this plane piece as an example, we can easily obtain the expression of pulse angle rate. Further, we can get the pulse angle rates on the three different motion cases, which are CV, CT, and CA motion. By comparing these three results, it can be seen that their pulse angle rates have significant differences, especially in the case of CT motion, where the second atom originates from the normal acceleration. After understanding the relationship between motion mode and the pulse angle, let's focus on the most sensitive signatures of the reader target, which are important for reader to perceive changes in target pulse and further correlate with motion modes. Here, we consider three signatures, which are reader cross-section series, angular glint, and Doppler profile. Based on reader intuition and multiple scatter centers impression, we can easily derive the target echo expression. Further, we can obtain the signatures of RCS series and angular glint according to their definitions. As shown in these three equations. Similarly, we can get the Doppler profile, which means the scatter center distribution with different Doppler frequencies, as this figure shows. In order to clarify the relationship of reader signatures and pulse angle rates more clearly, we consider an ideal target with two scatters locating along y-axis with a sensitivity, whose scattering intensities are isotropic. After some derivations, we can obtain the results as shown here. First, we can see that the time derivatives of RCS and glint are both proportional to the pulse angle rate, which means the greater the pulse rate, the more intense of these two signature change. Second, the last equation represents the difference of Doppler frequencies between two scatters, which is also proportional to the pulse angle rate, which means the greater the pulse rate, the higher the resolution of Doppler profile. In other words, these three signatures are sensitive to pulse angle rate and can be used to identify motion mode potentially. Next, let us study these reader signatures during different motion simulation. To better study, we used the GSD sim, a 6-degree of freedom flat dynamics simulation software, and a FlatGeo, a 3D flat simulation tool, to stimulate the target's flight state under different motion mode with high fidelity. Combined with the multiple center model of the target, we can acquire the corresponding media echo data and further extract the most sensitive signatures. Now, let's consider a specific scenario. In this scenario, a fighter with 68 pointer center flew in a CV motion mode, then switched to AT motion mode at 1 second. These figures show the simulation results of RCS signature. From them, we can easily find that whether the RCS series or the width of its autocorrelation function and power spectrum have a significant difference before and after maneuver. These figures show the results of glint signature. The simulcongruent RCS signature can be drawn. These figures show the results of the Doppler profile. From them, we can find that the Doppler profile in CV motion mode behaves an ideal pointer spread function, while the Doppler profiles in CT motion mode behave multiple scatter structure because their resolutions increase with both angle rate. Through these simulation results, the correlation between both sensitive signatures and motion modes was further verified. Now, we can answer where motion identification is based on media signature. That is, both sensitive media signatures are highly correlated to motion modes and quickly respond to motion mode change, so that they can be as a key input for quickly identifying motion mode. Next, let's discuss how to identify motion mode based on radar signature. On the aforementioned both sensitive signatures of radar target. Here, take maneuver detection problem as an example to illustrate motion mode identification based on radar signatures. We assume that the reader can acquire the target's RCS, angular glint, and Doppler profile, and that the target switches from the non-maneuvering mode, that is CV motion mode, to the maneuvering mode, that is CT motion mode, at a known time instant. Now, the problem is how to quickly detect an unknown maneuver. We designed the corresponding maneuver detectors for 3 different signatures, respectively. Then, based on proposed performance indices, we evaluate the performance of 3 signature-based maneuver detectors with state-of-the-art maneuver detector based on filtering residual information on motion state. First is maneuver detector based on RCS series. We used an equivalent FIR filter to extract the third detailed component of Dawkins wavelet for the RCS series. Then we learned the prior distributions for the non-maneuvering, that is 0, and maneuvering, that is H1, accesses by offline simulation samples. Finally, The feature-based sequential probability detail test method was proposed to determine whether the target is maneuvering. This method can effectively utilize the variation features of the process series, improving the timeliness and accuracy of maneuver detection. Second, is the maneuver detector based on the data series from the work of Hughes. He took the cumulative sum of square normalized points as test statistics and used a fuzzy logic detector to detect maneuver. The technical details are found in his doctoral dissertation. Third is the maneuver detector based on the Doppler profile. We extract two features of the Doppler profile, such as the number of peaks beyond the threshold, with a relative quotient of both sides of the peak position and the centroid position of Doppler profile. These features can fully reflect the changes in the Doppler profile before and after the target maneuver. Then, a BP neural network was used to classify the extract features, distinguishing the maneuvering and non-maneuvering motion modes of the target. To evaluate the performance of these detectors, we set a series of performance indicators, including detection probability, false alarm probability, and detection delay. Now, let's look through some results. These figures show runs of maneuver detection delay for three signature-based detector and C-mean detector, under the condition of a 1% false alarm probability. From them, we can easily find that three signature-based maneuver detectors have smaller detection delays than C-mean method, which means they can quickly respond when motion mode changes, especially the Doppler profile-based detector has the best performance because it used a BP neural network, which can learn the differences in Doppler profile and the different motion modes through training. To comprehensively evaluate the performance of several maneuver detectors, here we give the comparison signal for all performance indicators. We can see that signature-based detectors have superior performance than C-mean method and all performance indicators. These performance evaluation results provide an important basis for us to select appropriate detectors in practical applications. Finally, let's integrate signature-based maneuver detector into maneuvering target tracker. Let's consider the same scenario in the last section. Here are dynamic model and environment model for the tracker. For the dynamic model, we consider the CV model and CT models with different time directions. Here, we proposed a general framework shown in this figure in the FAAM tracker. By integrating the signature-based maneuver detection into variable structural multiple model VSMM tracker, one state-of-the-art maneuvering target tracking method. In this framework, the signature-based maneuver detector determines whether the target is maneuvering. According to its detection, the corresponding model sets M0 or M1 is selected for multiple model tracker. That is why we call it as feature-aided VSMM tracker. Let's compare FAVSMM tracker with the classical multiple model trackers. Here, we select a numerous multiple model that is EMM and interactive multiple model that is AMM. And the total profile of the maneuver detector was used. First, we give the variable curve the model probability with 10 of 3 trackers. We can conclude that FAVSMM has the best quickness and steady performance for model probability estimation or mode identification. Second, we give the result in state estimation error. By comparing the results, SMM can effectively reduce the position error and the velocity error during the target's maneuvering process, especially at the moment when the target motion swings. The FAVSMM can adjust the tracking model more quickly, reduce the error of the model mismatch, and finally improve state estimation accuracy. Finally, we integrate the FAVSMM tracker into the guidance loop and evaluated the average misdistance with different estimator configuration. The guidance law is a one-type differential law, and the baseline estimator is EMM tracker. The experimental results show that the average misdistance is basically insensitive to maneuver initial depth, and the average misdistance is reduced more than 50% compared with the EMM estimation configuration. This further proves the effectiveness of reader signature-based motion identification in improving the performance of maneuvering targeted tracking and its benefits to the interception tasks. Finally, let us conclude and with future research directions. Here, the main conclusions are listed as follows. We think that the future works can be done at least along these following 4 directions. The related published literature is given here. I hope they can provide provide some useful reference for our audience. That concludes my report today. Thank you for your attention. And I sincerely.
Thank you very much. Professor Pan. Probably audience have a question. Yes, Professor.
Thank you very much for your very interesting presentation, Professor Pan. I'm not really an expert in this subject, but it's clear that when you're trying to recognize motion of the target, you should also incorporate in some way the model of the target. I mean, you should also recognize first the target, create the model of the target, and then incorporate this part into your general algorithm for motion recognition, because the motion depends very much on the target itself. So is it done in your work, or maybe I mismatched during this presentation, recognition of the target incorporated into your motion recognition procedure?
Hello. Professor Pan, did you hear the question?
Yeah, I agree the professor's suggestion. I think the motion model recognition is a subject or sub-subject of target recognition. I think the motion mode, the identity and the type are also can include in the target recognition. Today, I explain my research mainly on target motion mode detection. It will be useful for the maneuvering target like I used today. And this information is also useful, as I see, for the more level situation evaluation, such as interception, such as target intention estimation, and the situation awareness. I think today I only introduced some part of the work. Thank you for your question.
Yes, I also support because not only to recognize motion type, but also to recognize object type, I mean target type, because knowing the object type, flight type and so on, we can also predict its motion and so on and so forth. So we are fully agreed together with you that we have to try to recognize object or target type also, and then to recognize its motion and so on and so forth. So we can work together for this task here. Okay, some other questions? No questions. Professor Fan, thank you very much for very interesting speech.
Thank you, Chairman. Thank you for your invitation.
Thank you. All the best for you, and we will continue.
Bye-bye.
Yeah, thank you. Bye-bye. We continue our speech. The second is Professor Dondon Lee. The title is Exploring Efficient and Effective Sequence Learning for Visual Object Tracking. And let me tell a little bit about Professor Dondon Lee. Also to introduce, he received Bachelor of Science from Wuhan University in 2012 and Master and PhD degrees from National University of Defense Technology in 2014 and 2018. During his PhD, he was a joint doctoral student of Australian National University also. Professor Lee research focuses on computer vision and machine vision, and he serves as associate editor of IIT Image Processing and YAS editor of the Chinese Journal of Information Fusion. He is also leader of the ATR Challenge, Automatic Target Recognition Algorithm Challenge, which tackles complex problems in target detection and recognition, and releases realistic application scenarios and datasets, and solicit innovative algorithms and solutions for target detection, tracking, and recognition. So, Professor Dondonli, welcome.
Okay. Hello. Okay. First, I'd like to thanks for the professor's introduction of me. Then I will start my report here. Good morning, everyone. I'm Dongdong Li from National University of Defense Technology in Changsha, China. First, I'd like to thank Akshay to offer me the chance to give a keynote speech here. Today, today I'll share this recent work from our group, which is started by the RDK 2025, titled "In Exploring Efficient and Effective Sequence Learning for Visual Object Tracking." In this talk, I will present our work from 4 aspects. First, I will introduce the background and motivation of single object tracking. Second, I will detail the core innovations of fast sequence track, which is the name of our work. Third, I will show the experimental validations and the results. Finally, I will conclude the presentation of our future work. Okay, now let's begin with the background and motivation. First, I'd like to introduce the definition of single object tracking for listeners who are not familiar with this task. The definition is that given the bounding box for the target in the first frame, as we can see in the above 3 videos, the task of single object tracking is to locate the trajectory of the target in the following video frames. The evaluation metric of single object tracking is by measuring the intersection over union, which is short for LU, of the estimated bounding box and the annotated ground truth. During tracking, the tracking model will face many challenging factors, including the first one, partial occlusion, the second one, illumination variation, the third one, motion blur, and the last one, small target size. All these challenges will lead to tracking failures in civil scenarios. Meanwhile, the inference speed of the tracking model must be higher than 30 frames per second for real-time applications. Therefore, it's really hard to make a good balance between tracking accuracy and tracking speed. Honestly speaking, there have been many existing tracking algorithms, among which SAMS-FC is one of the most famous. SAMS-FC is based on the SAMS-collusional neural networks, whose input is an exemplar template image Z and a search image X. The bound Z is cropped around the target in the first frame, while X, the image X, is cropped in the current frame. The output of the whole network is a heat map, whose peak is the estimated location of the target. Okay, let's go on. Nowadays, inspired by the multimodal large language model like DeepSeek or ChatGPT, Sequence learning-based trackers like SequTrack has been proposed and shown impressive performance. Its working pipeline is shown in the above video. The input data is the template image, the search image in the below, and a star token in the above. The sequence model estimates 4 values of the bounding box, namely x, y, WH, in an autoregressive manner. However, this autoregressive sequence generation manner leads to significant latency. As shown here, SequTrack generates the bounding box coordinates token by token, requiring the sequence model, which is a decoder, to run 4 times per frame. This serial process is a major bottleneck for real-time applications. So our key motivations is clear. Can we achieve high tracking accuracy while dramatically improving inference speed by eliminating their serial dependency? To be more specific, we face 2 main challenges. First, how to enable parallel generation of 4 bounding box coordinates to boost speed. Second, how to maintain or even improve accuracy despite the simplified, faster architecture. We need to ensure the model doesn't lose crucial information during the speed up. To tackle these challenges, we propose fast SequTrack, an efficient and effective sequence-to-sequence tracking framework. The core idea is very simple yet effective, which is parallel generation with better initialized tokens. Let me explain the core difference between SequTrack and the fast SequTrack. The SequTrack is on the left and the fast SequTrack is on the right. As illustrated, instead of starting with a single randomly initialized token, which is here in SequTrack, fast SequTrack introduced 4 learnable tracking tokens. Each token in fast SequTrack is responsible for predicting 1 dimension of the bounding box, x, y, w, and h. Okay, now here is the crucial part, the whole network architecture of fast SequTrack. These 4 tokens are not generated sequentially as in SequTrack. Instead, they are appended to the visual patch embeddings at the input stage and are jointly refined with the encoder itself. This means that the encoder, which is generally a vision transformer, not only extracts visual features but also provides a much better informed initialization for each of the 4 tracking tokens based on the context of both the template and search image. As a result of this better initialization, the subsequent process becomes much simpler. In this decoder, these 4 pre-refined tracking tokens are fed in parallel and processed in a single forward pass. They act as queries to attend to the visual features. Because they are initialized where and processed simultaneously, there's no need for the complex or the regressive loop. This one-pass generation is the key to our dramatic speed up. To further speed up the tracking speed, we also integrate a very famous mechanism called early exit. The idea is inspired by the concept of avoiding network overthinking. We attach a lightweight, parameter-free sharing embedding toward the network after each decoder layer. Sorry. After each decode layer, the network acts as an internal classifier, sampling each bounding box value and providing a confidence score. After each decoder layer, we compute the average confidence of the 4 predicted coordinates. If this average confidence exceeds a predefined threshold, it indicates that the current prediction is already reliable. Therefore, we can safely terminate the forward pass early and upload the results immediately, skipping the remaining decoder layers. This thematic inference is highly efficient. It saves significant computation on easy frames, while a few layers is sufficient, while still allowing the full network depth to handle complex challenging scenarios. Critically, because the embedding toward networks are parameter-free sharing, this mechanism adds no extra parameters to the whole model. Now let's turn to the experimental results. We evaluate our tracking model, FastSequTrack, on 4 major benchmarks: WASTRACK, TNL2K, TrackingNet, and GOT10K. The results are compelling. First, in terms of the tracking speed. Speed is very important for the tracking problem. In terms of tracking speed, as shown in the table, in the right part of the table, FastSequTrack runs at 125 FPS, more than twice as fast as the original SequTrack, which is only 58 FPS, thanks to the one-pass parallel generation. Second, in terms of accuracy, FastSequTrack achieves state-of-the-art performance across all benchmarks. This demonstrates that our parallel design and better token initialization not only speed up the inference, but also enhance tracking accuracy. The first rank is marked with red, and the second is marked with blue. Third is marked with green. So we can see that FastSequTrack almost achieved the first rank on almost all the metrics of 4 datasets. We also conduct attributed-based evaluation on the WASTRACK dataset. FastSequTrack achieves consistently high performance on all attributes, including aspect ratio change, background clutter, deformation, fast motion, invisibility, illumination variation, low resolution, motion blur, rotation, and skew variation. So it's very robust in challenging background. Finally, ablation studies confirm that the effectiveness of both parallel generation and the early exit mechanism. Removing either component leads to a drop in speed of performance. Okay, in conclusion, we have presented FastSequTrack, a normal and efficient tracking framework. To summarize our key contributions, we propose a one-pass parallel generation method for bounding box sequences, significantly boosting the inference speed. We introduce better initialized tracking tokens while encoder refinement improving accuracy. Third, we integrated a parameter-free early exit mechanism to further enhance efficiency in easy frames. FastSequTrack achieves real-time performance about 125 FPS while setting new SOTA results on multiple benchmarks, effectively bridging the gap between efficiency and accuracy. Okay, here are some plans for our field work. Our field work will include in 2 parts. The first part is to propose a multimodal general tracker for different applications. In fast-trip track, the input modality is only the visible modality, namely the RGB images. Therefore, we want to change the input, extend the input modality from visible image to visible infrared language or even the audio modality, because more modalities, more information, and the more information, the better performance in challenging environments. Here are some screenshots of the multimodal tracking dataset. The first on the left is the visible infrared tracking datasets, and on the right is the visible language and audio tracking dataset. Here is a new work from our group, which has been submitted to UIIP 2026. The input modalities are RGB, a visible image, infrared image, and language image. To adaptively select the best modality for tracking, we inject a mixture of experts into the vision transformer blocks, which is a common trick for multimodal large language model like GPT. Okay. The second part of our field work is embodied tracking for drones. As I remember, the Zhejiang University of Technology and UIIP has established a joint lab, Belarus-China joint lab for embodied intelligence. So we also have the plan to do job in embodied intelligence. We want to deploy the tracking model in the computing platform on drones and associate the tracking models with the control system of drones. It is something like the embodied intelligence, which is very hot at this moment. With the embodied tracking system, the camera or the drone can perform active tracking, which is to locate the target or following the target, just as shown in the video. We can locate the cab, and the drone can just follow the person on the ground or the cars on ground, and do some jobs like chasing or following the target. So it's the second part of our field work. Okay, here is the end of my presentation. Thanks for all of your attention.
Thank you very much for a very interesting presentation. Probably, audience, do you have questions?
Thank you very much. I also have a quite simple question. Yeah, because there are many now trackers developed for tracking objects, and I see that many of them are very stable, so they track very good. But in general case, but there are some difficult situations sometimes, right? When there are obstacles and the object is behind the obstacles, or several
distractors.
Yes, or they are joined together, and then it's necessary to make some decisions. So is your tracker is in some way intellectual one? It's also not only like predicts these coordinates and bounding box size, but also did some more intellectual recognition of the object, which is tracked, or you just tracking the object and do not recognize it at all?
Okay. First, I'd like to mention that our research is called model-free single-object tracking in the literature. Model-free means that we can track anything, any object, despite its category. So we only do the job of locating. We don't recognize. Of course, if you track the object, you can crop the bounding box and input it to some networks to do some recognition jobs. Okay, this is the first question. The second question is that your question is very important and tricky. That some trackers are easy to drift or tracking failures during tracking. For example, if there is some occlusion, partial or full closure, the tracker will lose target. Or if there are some distractors, for example, I will track person A. If person A and person B just cross, the tracker maybe drift to the other person. Yes, it's a very old question, but very hard to solve. So, as I mentioned in this slide, our solution is that only the visible video as input is hard to track robustly. So we want to add other modalities. For example, in case of partial occlusion, we will input not only the visible video, we also input the depth video. Yeah, it's another kind of sensor. So just with the RGB image and the depth image, we can recognize what time there is an obstacle and track just robustly. In case of the distractors, we can add not only the RGB image, we can also add the infrared image, because if person A and person B are very similar in appearance, but their temperature maybe is different. So if we add the sensor of the infrared camera, we can maybe add more appearance information to the tracker and teach the tracker to track robust in these cases.
Okay, thank you very much. Some more questions? Okay, please.
Hello, thank you very much for an interesting report and macro results. Could you please give more details about early stopping exit block in your network? Early stopping.
Sorry, could you repeat the question again?
Early stopping block in network architecture. Could you please give us more detail how it realizes, or maybe give some practical examples how it looks in real cases?
Block, what block?
Early stopping, early exit block.
Был на слайде где-то он, да?
Yeah.
Can you show different slides?
With main architecture of fast sec track.
Which slide?
Here, yes.
Not here.
Yes. Early exit block.
Early exit block, this one.
How it is
Early exit block.
Okay.
He wants a question about a little more.
Could you give us please example how it look on practice, how it works in practice, in practical?
Okay, maybe I will give more details for the network architecture. Okay. Okay, let's start from the bottom to the top. In the bottom, the input to this network is a template image, a search image. The template image is cropped from the first frame as the appearance information for the target. The third image is cropped from the current frame. So we can just input these two images to a backbone network, which is always implemented with a ResNet or vision transformer. So, the information from the template and search image can be fused in the transformer encoder to extract the visual embeddings. Then here are some different from the secret track. contribution of our work is that we input the tracking tokens which are initialized with random. And we import the tracking token and visual information both to the transformer encoder. So the tracking tokens will attend to the visual embeddings and learn something from the pictures. And this is the first stage. In the second stage, the tracking tokens are changed into queries. These queries are randomly initialized in SigTrack, but in our network, it is firstly fused with the pictures, so it's better. So in the second, it's almost the same with SigTrack, because in the second, which is a decoder, the queries will attend to the visual features from the search image. It will attend to the visual feature from the search image, and the decoder will output the final queries and regress these queries to the 4 values of the bounding box. This is the whole pipeline of our network.
Okay, thank you.
Okay, thanks for your question.
Okay, no more questions? Okay, thank you very much again, Professor Gondon. Okay, we have morning coffee, let's say 15-20 minutes, and then we will continue after the break. Thank you.
the bison. Where rivers are deep and skies are high. History. Embedding the future.
Dear colleagues, so we continue our morning sessions, and now I would love to start a session which will be conducted, managed by our previously plenary session speaker, Don Lee. So you already know him as an assistant professor of the National University of Defense Technologies, very brilliant researcher. So he will manage the session with his colleagues directly from Changsha. Yes, so, well, Chairman, you have a floor.
Okay, thanks for everyone for being here for this session. I'm glad to be the session chair for this moment. In this session, we will have about 7 reports in this session. Now let's move on to the first one. The first presentation is titled 3D Vision Simulator for Multi-Camera Systems by Qiming. Hi, Qiming, are you there? No voice. You can start your presentation. There's still no voice in your video. Problem here, right? 启明，你等一下，你们那没问题。Sorry for the audience, there's some technical mistake in this conference venue at the moment.
Test. Can you say something?
启明，你们那儿要播放视频看一下，现在可能快好了。
Turn on microphone.
Good morning, everyone. I'm excited to share our work titled MCS Theme, a 3D VR simulator for multi-camera systems. My report is divided into 4 parts. The first part is source of the problem. Right now, autonomous unmanned systems are advancing fast. UAVs, in particular, are getting a lot of attention in the low-altitude economy, like for package delivery and night shoots. Autonomous unmanned systems usually have several key parts: sensors for detecting the environment, position and mapping, scene understanding, planning, control, and communication. Among these, sensory is the most critical. It's the foundation for getting the job done, and it relies on different types of sensors. Perception sensors come in many types, like a visible light, radar, or LiDAR. Among these, visible light sensors are the most common because they are cheap and provide rich information. Today, most VR sensors use single or stereo cameras, but they have a narrow field of view. Fisheye cameras widen the field of view, but they lose some resolution due to physical limits. To solve this, multi-camera systems now combine high resolution, wide field of view, and depth sensing. They are used in areas like computational imaging, simultaneous localization and mapping, and autonomous driving cars. Multi-camera systems research faces 3 big challenges. First, physical error. Setting up a real camera takes too much time and money. We need simulation tools to test designs faster. Second, algorithm error. Developing algorithms requires real-world data, but those sets are hard to find. Third, application error. Testing complex systems can be dangerous and costly. To solve these problems, we have created a multi-camera system simulator. It speeds up research by providing virtual testing environments. To simulate UAV multi-camera perception, these tools must include some key features, including sensor simulation, UAV simulation, dataset generation, dynamic object simulation, and diverse scenario configuration. Together, these help researchers test and improve perception systems faster and cheaper. The second part is related works. Simulators with 3D engines help create synthetic data tailored to specific needs. These tools mainly do 2 things. First, vision-oriented simulators. They generate realistic-looking images with accurate neighbors for training models. Second, physics-based simulators. They focus on how objects and environments interact physically, which is key for robots and AI that moves and acts in the real world. Neural closed-loop simulators inspired by neural vision spheres and 3D Gaussian splatting. We construct real-world environments for autonomous driving applications. Since 2024, video diffusion models have advanced quickly. They can now generate highly realistic driving scenes. One example is Drive Alana, a simulator that uses these models to create virtual driving environments. Each existing simulator has distinct advantages and drawbacks, as shown in the above table. Wheel-oriented and physics-based simulators leverage mature graphical pipelines to create highly accurate scenes, maintaining spatial temporal consistency while providing pixel-wise annotations. These simulators run mostly on ordinary laptops with GPUs, makes them widely accessible. In contrast, neural and generative closed-loop simulators, which have emerged only in the past 2 years, produce high fidelity image quality. However, they suffer from inherent geometric inaccuracies, leading to rendering artifacts and spatial temporal inconsistencies, with compromised pixel-wise annotation accuracy. Moreover, they require powerful desktop calculators and often can't run in real time. The third part is specific content. The overview of simulator architecture is presented above. Developed using Unity Engine and Qt Designer, the simulator includes some lead paths: simulation setting, multi-camera system model, UAV control, image data generation and recording, closed-loop testing. Our innovation has 3 parts. First, a modular simulator architecture is introduced that extends conventional molecular simulation paradigms to multi-camera configurations. First, the second is a structured synthetic dataset generation pipeline is integrated to output multi-camera sequences with multimodal piecewise ground truth. Third, a hardware-in-the-loop interface is developed to enable end-to-end system testing. This demonstrates the execution showcase from top to bottom, showing sensor simulation according to an artificial composite eye system, UAV simulation, and dataset generation with 4 piecewise annotations. As an example, according to this table, we simulated a multi-camera system with a cylinder RentNet and angular cameras. Then, 6 sequences are generated with 3 scenarios and 2 motion patterns as a demo synthetic dataset. For visual perception algorithms test, the demo datasets are used to test some visual perception algorithms. The purpose is to show how useful our simulator is, not introduce new algorithms. For dense motion flow estimation, 2 representative methods, RAST and rough 3D are evaluated. For multi-camera depth estimation, two surround multi-camera methods are evaluated: surround depth and R3D3. For visual step, these methods ORB step 2, stereo, DSO, and R3D3 are selected as the subjects for this testing. Closed-loop simulation creates a real-time feedback loop between virtual environments and tested systems. In the figure, solid lines represent data stream between hardware entities. Solid arrow dashed lines denote serial communication data stream between the simulator and hardware entities. And hollow arrow dashed lines indicate the injection data stream. The simulated visual sensor injects rendered images in real time into the photoelectric data processing device. Simultaneously, it sends status parameters to both the photoelectric data processing device and the flight control device. After calculations by the embedded visual perception algorithm, the photoelectric data processing device feeds the processed information back to the flight control device and the ground station. The fourth part is summary and outlook. Compared with the existing simulators, our incremental work is adding arbitrary multi-camera system configuration, and visual dataset generation, and hardware in-loop simulation interface. In the future, we will combine with new technologies to enhance the simulator, integrate generative AI into simulations, enrich 3D assets and 3D scenes, combination of 3D modeling and neural rendering, such as NERF, 3DGS. I'm very glad to make this report. Thank you.
Okay, thanks for your report. Now it's question time. Any questions? Okay. Thanks for your report. It's very interesting. I've got one question. Which is how to solve the model generalization problem in your system, because the simulated data is quite different from the real world data.
For this problem, I think our simulator is proved tool to synthetic data set for pre-training. Some algorithms has tried to use a great amount of synthetic data set to enhance their performance. For example, the depth estimation algorithm, depth anything, V2, and this algorithm first use lots of synthetic data set for training, and because some annotation like piecewise depth and segmentation is is not available for real thing data set.
Okay, thanks for your question. Thanks for your question and excellent work. Okay, due to time limits, let's move on to the next report titled Joint Region Angle Ambitious Estimation based on DASPO OMP for FDA memo reader. Okay, you can start now.
Hello everyone, I'm Colin from China, and I'm honored to be here to show my work. The topic of my presentation is joint range angle ambiguous estimation based on DAPSO-OMP for FDA memo reader. This is my email if you want to contact me. There are 4 parts here. The first part is an introduction to my work. FDA reader is firstly proposed in 2006, which employs a frequency increment across the transmitting elements, so it can provide an innovative solution for full spatial observation by flexible beam scanning. In recent years, many scholars have paid attention to memo readers' high degree of freedom, which has led to the emergence of FDA memo reader that combines FDA with memo. Different from the existing reader, the FDA memo reader forms a joint mature steering vector at the transmitter and the receiver. Thus, the decoupling of target, range, and angle is achieved, and finally, a more controllable beam pattern is obtained in the 2-dimensional domain. The second part is the work related to my work. In the existing work, the pyramid estimation of FDA memo reader mostly focus on the linear frequency offset, which often leads to the large side lobes. But in recent years, some scholars have proposed the linear frequency offset to decouple the range and angle of the pattern. However, the estimation accuracy of these algorithms is poor, and the conditions of noising and small snapshots. In the problem of target pyramid estimation, these methods have the problems of high side lobe and large space coverage loss. In order to solve these problems, we have carried out corresponding work recently. The third part is the structure of our algorithm. Compared with the traditional linear frequency offset and FDA memo reader, our work is based on the derivation of random logarithmic frequency offset and FDA memo reader. These are some derived formulas. It can be seen from the 2 forming that the items caused by the randomness do not form arithmetic progression. So we have solved the problem of range ambiguity. Based on resolving range ambiguity model, we derived the first-order approximate range angle mesh generation model. Firstly, we meshed the 2-dimensional space to build a super complete dictionary. Secondly, we introduced the grid error offset for range and angle parameters. Then we carry out the first-order Taylor expression on the Stirling vector of the ecosystem signal. Through a series of theoretical derivations, we finally get the optimized super-complete dictionary and transform the eco-signal model into an optimization problems. Based on the above two models, we propose depth-of-amp algorithm and give the float chart of the algorithm. The founding of the algorithm is double prism adaptive particle swarm optimization orthogonal matching pursuit. The algorithm can achieve more effective and accurate range angle joint estimation by setting the two double precision scale. It can not only maintain high estimation accuracy and the limited number of snapshots, but also significantly reduce the demand of compute resources. The first part is the simulation and the prospectation. We first give the simulation parameters of FDM memory data and the initial conditions of the algorithm, such as carrier frequency, cross duration, frequency increment, bandwidth, transmit element size, receive element size, and so on. This is the joint range angle parameter estimation result of depth-of-amp algorithm and different small snapshots and no scenes conditions. We have set 3 targets. From the estimation results, we can see that the side loop peak control is very low, and there is no target with range ambiguity. It can be seen from the estimation result table that the estimation accuracy is still very good, even under the condition of a signal snapshot and -10 decibel. In order to verify the performance of the algorithm in solving range ambiguity, we set up a group of experiments. Similarly, we set 3 targets, but the parameters are different from the previous group of experiments. The first is linear frequency offset. The second is random logarithmic frequency offset. From the figure A, you can see that the target estimation of the result of linear frequency offset is ambiguous, while the result estimation of random logarithmic frequency offset is accurate. Through the comparison of linear frequency offset and the random logarithmic frequency offset, it can be seen that the algorithm has a good effect on the range ambiguity. In order to verify the limited performance of the algorithm, finally, we compare the MSE results of different algorithms, include depth of OMP, post-OMP, and OMP. In order to make the results more reliable, we set SNR and snapshots tests for both range and angle estimation, such as MSE of range with SNR, MSE of angle with SNR, MSE of range with snapshots, MSE of angle with snapshots. The result shows that the MSE of the algorithm is the smallest in both the range dimension and the angle dimension. This paper proposes a range ambiguity depth of OMP algorithm for FDM memory data. The reserving part of FDM memory data based on random logarithmic frequency offset is derived to solve range ambiguity.
On this basis, the depth OMP algorithm further improves the speed and the position update formulas by adopting a dual position iterative method to enhance the convergence in speed and the global optimal solution search ability of the algorithm, thereby accelerating the optimization process of ARM and reducing computational complexity. Finally, through complexity analysis and simulation experiments, it is verified that the depth OMP algorithm proposed in this paper has better estimation algorithm and robustness compared to the post-OMP and OMP algorithms. Okay, this is all my work. Thanks for your listening.
Okay, thanks for your report. Any questions? Okay.
Very small question I have. Because you do some range angle estimation, but it means that you should have in mind one target which you estimate, yes? So
yes.
This is, can you say anything about this kind of targets? I understand that it might be something like not for open auditory information, but maybe some civilian examples.
Okay, Professor?
Yes.
Professor?
Yes.
What's your problem?
The question is like, because you explain us how you do a range angle estimation for your problem from your data, but the targets for which you estimate this kind of information, can you say anything if it's like open information? And maybe do some example of civilian targets which you would like to estimate parameters.
Okay. Thanks for your question. In the future, I will open my information in the website or on the paper.
Okay, thank you.
Thanks for your answer. It's very short and brief. Okay. Due to time limit, we will just move on to the next report titled "Leverage Semantic Pride from SAM for Super Resolution" by Baiheng. You can start your report now. Hi, Baiheng, are you there?
Yeah.
First of all, come to the introduction part. Image super resolution aims to recover HR from LR count dots. So you can see after image super resolution, the image becomes clearer and have more details. But SR model looks the ability to identify the category of idioms and always share the same pattern. The similar object, as you can see from the wall, where it with the prior that become more artifacts, and with the building prior, it can reconstruct a better image. So introduce semantic prior into the network is very helpful. How to introduce semantic prior? Intrinsically, we want to tell the model the region that about its object and category, and leverage semantic segmentation is what we need to better leverage semantic segmentation prior. We will turn to one of the most powerful model, SAM, segment everything model, a large model that is robust and accurate. So a good form to leverage this model is to let it know what it is. It's about the category, and where is similar is also about the category. Let me tell you carefully how to. The two key questions is how to let the model know where is similar and cluster region with similar semantic, so that it can know what is the semantic prior. How to understand this question? As you can see from the red rectangle, the SAM segmented the whole image into many patches, but the same semantic prior, like the trees, is not continuous in some segmentation. So we must cluster all the trees patches into the same patches, so it can learn about the semantic of the tree and divide it from other things like grass or dogs. That is to let the model know where is similar and what is the semantic prior. Now the two questions, the second question is how to leverage segmentation from information. As you can see, SAM, after segment anything model, the semantic prior is shown in the form of one hot matrix. It's a mask of segmentations. So how to leverage this kind of information with the image prior? We can think of a lot of things, but which is the best? So our target is to investigate semantic prior from SAM utilization to enhance super resolution models and let it know what it is and where it's similar. In our work, our contribution has two main contributions. We proposed a channel enhancement model and a semantic fusion model to separately solve the question of what it is and where it's similar, and solve the question of how to fuse the semantic encodings with image feature maps. Okay, let's answer the first question. To answer this question, we use channel enhancement model. So we can see in the mask of the segmentations, it is the one hot matrix, and every channel represents one instance. So if we want to get the difference and to find where to cluster the instance, it is to do the correlation operation. And when you're talking about the channel correlation operation, we can firstly think about channel attention mechanism. So we use channel attention to do that. The second question is to leverage semantic form information. Since the mask of the segmentations is a one hot matrix, and the image map is also a matrix with 3 dimensions or 4 dimensions. So we can use cross-attention mechanism to align them. Cross-attention can easily align and fuse them. As you can see, they can first concave and through a convolution block. And also we need to do some transforms to the mask of the segmentations. After that, we use them to perform multiply and also convolution block. After that, we can complete them to the next block for better fusion. After introducing the two small model, we can see our whole unit, the semantic prior fusion unit. We propose this effective unit for using the semantic prior in a form of one-hot mask with image feature maps. As you can see, this SPFU is used with two blocks. The first is the channel enhancement model for clustering semantic information from SAM outputs by instance. And the second is XFM, semantic fusion model, is to use for with the prior with feature. Let me tell the truth that the only SPFAU will not be very helpful. It must be an alternative strategy that can better inject semantic prior into a super resolution model. And our proposed SPFU is, you can see it's plug and play. So this model can easily transform to other baseline model. Let's come to the experiment part. We use IFRK PRIP'2K as the training data set, and we use set 5, set 14, urban 100, manga 109 as the testing data set. We use BDSR and IMDN as a baseline model. As you can see, we achieved good scores, and in some of them, we even get a score of PSNR, data PSNR up to 0.2 dB. Let's see our validation study. For the first one, we studied the effectiveness of our proposed model. As you can see, we do 3 separately experiments. The first is do not concatenate the semantic prior with image feature maps. The second is have we remove the CEM model, and the third is to remove SF model. As you can see, the standard is always the best, and without computation will be the wrongest idea. So you can see the one-hot matrix is very quite similar with image feature maps. The second validation study is to study the optimal value of the weighting coefficiency. As you can see, we tried 4 kind of weights, and from small to is to 0.1 to 10. As you can see, when alpha equals to 1, this is the best PSNR we got. And too large or too small is not good for this model to run. And also, the impact of segmentation granularity in SAM is very important. You can see SAM can generate very fine-grained masks or coarse-grained. So we studied the 2 kinds of masks. The coarse-grained achieves slightly lower PSNR compared to fine-grained. So it is simply that the finer of the semantic prior, the score is much better. The last picture is about the qualitative comparison. As you can see, with our model, the picture becomes more clear and more details. Thank you for your listening.
Okay, thanks for your report. Any questions?
I have a small question.
Okay.
Okay, thank you very much for your presentation. I'm not an expert, but have the following question. So when you are trying to get a high resolution images from low resolution, you use this semantic information. So in your case, the quality will depend of high resolution images will depend very much on how good is this semantic information. So in your case, semantic information is some database of images, or you have other also options to process semantic data, not like some database of special images, which you have to like choose for your case and to improve the resolution of your data. Can you say a couple of words about your semantic data? In which form you prepare this semantic information?
Hello.
Yes.
I'm so sorry. I have trouble in adjusting the screen, so I missed your question. Could you please repeat it again?
Okay. Just to make my question short, I would like to ask you to say a couple of words about the semantic information. In which form do you prepare this semantic data? Do you have a big database of semantic images, or you have some other formats of data you use as semantic information?
Okay, I understand your question. That's a good question. For semantic prior, we can, in our opinion, we divide it in two parts. The first part is we can think it as a high-level operation for the images, and to describe something we can describe in language such as trees, banded in texture, and this is one kind of semantic prior. And the other kind of semantic prior, we can call it text prior, which is formed as character. So when talking about the semantic prior, the multimodal prior, which is text prior, is much more difficult to leverage. So we tried this semantic prior in picture form. That is we call the one-hot matrix tensor, which is generated by semantic anything model. That's why we choose this format of semantic prior. And we will do the experiment for the text informed prior in the future work. And thanks for your suggestion.
Okay.
So it means that you can have several channels of semantic information. You can have in the form of images, you can generate semantic information, but you have to make some decision which semantic information is best one for your case of your low resolution images. How do you do this decision? You told me that you have multimodal, yes, options for generating semantic information. Multimodal. You can generate it, you can have some database of images, but you have to make some decision which semantic information fits to your low resolution images best of all. How it is done in your case?
Okay, thanks for your question. Do you mean why we choose SAM for this super resolution model?
No, I do not know the details. maybe SEM is like just the best way to use in your case. But you can generate or can extract some semantic information from various channels. I mean, not just using like 70s, but you can maybe have a database of images. You know that your low resolution belongs to this kind of images. You can extract some semantic from this database of images. But so in this case you will have in some ways two channels of semantic information that you will have to decide which one to use for your low resolution images. But I'm not an expert, so I just asking you about this. Semantic SEM is like the unique way for you to prepare this data, and it is okay. It works very good, probably.
If we use the data sets of semantic data sets, we just limit our domain into a very small image feature domain. So if we use SEM, we can adaptively leverage all kinds of input images. This is much better for super resolution to learn a much good image features. Thank you for your question.
Okay, due to time limit, we will move on to the next report titled MCDSO. Hello, Han Yonglei, you can start your report now.
Okay.
Hello everyone. Today I will present our work titled MCDSO, a direct visual SLAM system for wilderness environments using multiple cameras. As shown on this slide, we'll progress through three parts. First, I'll provide some background. Visual SLAM systems are valuable because they are resistant to interference and require low-cost hardware. They have strong application potential in complex outdoor environments. However, existing monocular and stereo vision systems have limitations. Their field of view is restricted, and scale ambiguity remains a challenge. These issues make it hard to meet the robustness requirements of outdoor scenarios. In contrast, multi-camera visual SLAM offers clear advantages. It uses cooperative perception across multiple views to maintain environmental awareness, even if some cameras fail. Cross-camera feature associations further improve pose estimation accuracy. As a result, this approach shows great technological potential. However, when the number of cameras in a multi-camera SLAM system increases, the amount of image data and computational parameters also grows exponentially. Most current research tries to deal with this problem by focusing on sparse points of interest. This strategy helps meet the real-time performance requirements. The idea is to simplify rich pixel information into a smaller set of feature data. Cross-camera associations are then made through feature descriptors, but this method still faces two major challenges. First, feature extraction and matching are very computationally expensive. Second, these methods often fail in environments with poor textures. To address these challenges, we propose the MCDSO. The core contributions of the MCDSO system are as follows. First, we introduce optical flow estimation to replace traditional feature matching, establishing motion consistency constraints at the pixel level. This effectively resolves tracking failures caused by insufficient corner features in weakly textured areas such as grasslands and sandy terrain. Second, we establish a multi-camera geometric constraint optimization framework based on a rigidly coupled camera model. This enhances pose estimation accuracy through multi-view collaborative perception. Specifically, during local tracking, the system estimates pose by minimizing the photometric error. This process does not rely on feature points. As shown in the figure, a point from the local map is projected onto the target frame based on the initial pose estimate. In theory, the pixel intensities of the 2 points should be similar. To measure this, the system computes a weighted sum of squared differences within a small neighborhood around the point. Finally, it adds up the photometric errors of all points to obtain the interframe photometric error. After completing local tracking, the system applies an additional step to improve localization accuracy. It uses a strong prior constraint. The relative positions of all cameras on the rigid body remain fixed at all times. Based on this principle, a multi-camera joint optimization module is designed as shown in the optimization function. The poses of each camera from local tracking are transformed into the coordinate system of a virtual optical center. In theory, all transformed poses should be perfectly consistent. By minimizing the differences among them, the system obtains more accurate camera poses. This process effectively fuses information from all cameras. Next, we will evaluate the system's performance. We created a tri-camera simulation dataset using MCS to evaluate our proposed algorithm. In the MCS simulation environment, we deployed a coplanar tri-camera system with a horizontal baseline configuration. The baseline length between adjacent cameras was 0.5 meters. Focal length was 4.52 millimeters. The field of view was 53.13 by 53.13 degrees. The resolution was 700 by 600 pixels, and the frequency was 25 hertz. This camera system was rigidly mounted on a simulated quadcopter platform. The drone followed a predefined U-shaped trajectory, maintained a constant speed of 10 meters per second at an altitude of 50 meters. To test the effectiveness of the multi-camera improvements, we compared our method with the baseline DSO light algorithm. We labeled the cameras as follows. The central camera was 0, and the two side cameras were 1 and 2. The dataset was divided into 2 groups. Group 1, 0, and Group 0, 2 were used to run the stereo DSO light algorithm. In contrast, MCDSO directly processed the data from all 3 cameras. For evaluation, we used absolute pose error as the metric. These 2 figures show the comparison between DSO light and the reference values on the airport dataset. As the results indicate, DSO light produces small errors at the beginning of the U-shaped straight sections. At the trajectories and inflection points, the errors become much larger. These errors continue to accumulate, which eventually causes trajectory drift. In comparison, MCDSO shows much smaller errors at the trajectory inflection points. The right figure highlights the clear gap in accuracy between the 2 methods. The experimental results show that the absolute pose errors of DSO light of camera groups 1, 0, and 0, 2 are higher than those of MCDSO. This is because MCDSO directly processes the data from all 3 cameras. Overall, the MCDSO algorithm achieves superior positioning accuracy The table shows quantitative results of the absolute pose error. The maximum error is greatly reduced from 172 and 125 down to 30. The root mean square error, RMSE, also improved significantly from 92 and 68 down to 12. These results clearly demonstrate that the proposed MCDSO achieves superior localization accuracy. That brings me to the end of my presentation.
Okay, thanks for your report. And questions?
I have a question, yes. Also a small one. So please tell us how many cameras you mean when you speak about multi-cameras. Just your experience. 2, 3, 4. How many cameras first? And the second question is, as far as I understood, you already assumed that the position of the cameras, one respect the other, is fixed, yes? You do not consider the case when you have like flexible cameras, which are like not only calibrated, but they are in like flexible position, one concerning the others.
Professor, I think multi-camera is up to 3 camera. We think it is multi-camera. And the second question, could you repeat your second question?
So I assume if you have, for example, 3 cameras, right? For example, 3 cameras. So the mutual position of the cameras is fixed, and they are already calibrated, these cameras. Or you also consider the case when the camera, 3 cameras are like in flexible position, and you can just, for example, they change position with respect to cameras, and you can also simulate this 3D reconstruction process.
Okay, Professor. Our multi-camera system is fixed. We need the pre-calibration, so it is fixed. Yeah.
So you do not do inside your algorithm calibration of the camera from the like aligning the images which you get by this camera. So you consider the fixed case and pre-calibrated cameras, right?
Yes, yes.
Yeah, okay, thank you.
Okay, due to time.
Thank you for your question.
Okay, thanks for your answer. Due to time limit, we'll move on to the next report, titled Efficient Light Field Image Super Resolution with Shared Attention Transformers by Zhou Jiwei. You can start the report now.
Good morning, everyone. It's an honor to attend your PRIP 2025. My research topic is efficient light image super resolution with shared attention transformers. I'm Zhou Jiwei, the presenter of this work. The presentation is divided into 4 sections. Part 1, Introduction. Traditional optical imaging cameras can only capture the spatial information of light rays, whereas light field cameras, due to their unique mechanisms or array designs, can record both the spatial and angular information of light rays. Consequently, it possesses a wide range of applications such as focusing and depth estimation. In the field of image super resolution, single image super resolution methods are more frequent. However, compared to light field super resolution, Its methods suffer from insufficient prior information obtained from traditional cameras, leading to blurred or distorted super-resolution results. Therefore, effects of using images captured by wide-field cameras to acquire coupled spatial angular information and combining it with wide-field super-resolution algorithms to obtain high-resolution images hold significant application for you. Traditional wide-field super-resolution techniques can be divided into two categories. Below are two wide-field super-resolution methods and their classical algorithms. First, CNN-based methods. CNNs became the early mainstream approach by leveraging their powerful local feature extraction capabilities, such as LFCN, ISLM, distant SSR. Core advantage: efficient utilization of spatial locality but struggled to model long-range dependencies between views. Second, transformer-based methods. Transformers overcome the limitation of CNNs through global modeling enabled by self-attention mechanisms, such as LFT, DPT, and EPIT. The existing transformer-based LF and HSR methods generally face the problems of a high consumption of computational resource and high training difficulties. And the multi-layer transformer structure generally suffers from excessive interlayer attentional similarity, which leads to a serious waste of computational resource. For this problem, our contribution can be summarized below. First, we propose a simple yet effective backbreaking method for efficient LF image sensor. Second, we perform attention map sharing to effectively reduce the computational resource consumption. Third, extensive experiments on public datasets demonstrate that our method can achieve comparable SR efficiencies, significantly reduce computational costs. Part 2, proposed method. First, we introduce the schematic notations. Multiplication sign indicates computed attention maps. Minus sign denotes reuse of the corresponding reveals layer attention map, or you can tell by color. We propose some method primarily modifies the weight computation mechanism. In the original LFT spatial angular alternating transformer framework, every layer requires substantial computation, a highly time-consuming process that critically contributes to training difficulties at prolonged inference time. To address this, we guide greatly reduce by analyzing inter-layer attention weight similarity via average concise similarity matrix. It leads to two lightweight variants. LFT multi-page computes attention weights only in the first layer. LFT multi-4, all layers compute weights, and layers are reduced in previous ones. Part 3, experiments and results. The following presents the results of the cosine similarity analysis. The top two figures display heat maps for the average angular attention weight similarity and the average spatial attention weight similarity, respectively. A similarity value closer to 1 indicates a higher similarity. For spatial attention weights, the average cosine similarity between the first layer and the other layers exists 0.9 approaching 1. For angular attention weights, also the average cosine similarity is not as high as spatial level. It is still relatively large. Therefore, it is feasible to calculate the attention weights only for the first layer and reduce these weights to subsequent layers. The table below shows PSNR, SSIM reduced across different test sets under 2x super resolution conditions. PSNR is on the left, SSIM on the right, with the best result highlighted in red. This study produces existing algorithms on the same training and testing datasets, comparing them with the proposed lightweight method. As shown in the table, the lightweight LFT achieves competitive results against the state-of-the-art algorithms. Qualitative testing results across two scenarios are presented below. The inset on the right shows a magnified view of the left image. Below each inset are the applied methods, along with the PSNR and SSIM of the output images. The lightweight methods LFT-MLT8 and LFT-MLT4 proposed in this study exhibit no noticeable visual differences from the original LFT, and both achieve satisfactory super-resolution results. Critically, our lightweight model LFT-MLT8, which computes attention weights only in the first layer, achieves remarkable inference acceleration. Specifically, the sessions runtime by 53.4%, reducing latency from 0.2089 seconds to just 0.0973 seconds. Despite this drastic speed up, the performance compromise remains minimal, averaging just a 0.27 dB PSNR across 5 datasets. This validates our core innovation, the weight shelving strategy, by reducing attention maps across transformer layers. This approach delivers substantial computational savings while preserving image quality. Further refining this paradigm, LFT-MLT4, where all the layers compute weights and even layers use them, provides effective performance compensation. Part 4, conclusion and future work. All in all, we present a multi-layer transformer approach that is realized by attention weight shelving and applied to the LFT architecture. Furthermore, we compensate for the performance needs by varying the weight shelving method. Experiments shows that our weight shelving method significantly reduces the computation cost of them with minimal quality use. Follow-up studies should explore the generability of this weight shelving paradigm across different layer transformer architectures and verify its potential effectiveness in accelerating model convergence.
Okay, thanks for your report. Any questions? Okay, now let's move on to the next report. Next report is titled Design and Verification of a Centralized Multi-Agent Visual SLAM System Based on Cloud-Native Architecture by Yulian. Hi Yulian, you can start your report now.
Hello everyone, my name is Julian, and today I am honored to present the paper titled Design and Verification of a Centralized Multi-Agent Visual SLAM System Based on Cloud-Native Architecture. This work was co-authored by Yulian, Fan Hongyi, Dongxing, Jia and Wanghua Yan from the National University of Defense Technology. I'll cover 4 main parts: introduction, system architecture, experiments, and conclusion. First, the introduction of visual SLAM for multi-robot cooperation mapping. SLAM is key for mobile robots to navigate autonomously. It lets them figure out where they are and map their surroundings in real time, giving them a sense of their environment. Visual SLAM uses cameras to sense the environment. It's a good choice because it's cost-effective and provides detailed information. However, a single robot working in a large, complex area often has problems. Its own computing power can be limited, and its estimated position can drift over time. Using multiple robots together can help with some issues, but it creates new difficulties. Combining each robot's individual map into one global map requires a lot of computing. This uses a lot of resources, makes map building of resources, makes map building slow, and causes problems with real-time performance. This leads to the main goal of our research, solving the challenges of map fragmentation, position drift, and limited computing power on the edge devices in multi-robot SLAM systems. Let me introduce the system architecture in detail, and I will introduce it from two aspects: cloud edge collaboration and map fusion. To solve these problems, we built a new system for robots to work together using the cloud. Our system has three main parts working together: the edge, the cloud, and the connections between them. The key idea is simple, that the powerful cloud computers handle the heavy calculations so the robots can stay light and fast. Here's how it works. The edge layer. These are our mobile robots like Turtlebot 4 with depth cameras. They only do simple jobs, grabbing sensor data and doing basic feature spotting right away. The data transport layer. This layer uses ROS communication to send the video from the robots up to the cloud layer. This is where the tough computing happens. We use the cloud to do things like matching features across different robots, figuring out how all the robots are positioned relative to each other, combining everyone's individual maps into one big shared map. Then, the cloud sends back position updates to the robots. This setup keeps the robots simple and nimble, while using the cloud's massive computing power to do the complex stuff. An important part of our system is the map combining system. The hard part is to line up and combine maps from different robots efficiently. Our system does this by turning 3D point data into 2D grids. We use special tools we built with ROS to do this. We follow two important rules for this method. First, dynamic probability modeling. Each grid square starts as unknown, and we update its value as we get more point data. Second, step-by-step improvement. Instead of rebuilding the whole map every time we get new data, we use a continuous method to update only the parts that need it. This cuts down a lot on computer work. How we combine the map is simple. If one map has data on a grid square and the other doesn't, we use the data we have. If both have data, we take the average of their numbers. This lets us build a complete overall map step by step. Part 3. In this part, simulation experiments are carried out and the results are analyzed. To check if our suggested system design works, we did a set of simulation tests. We used the Turtlebot for mobile robots in the Gazebo simulation tool. This tool copied a common organized indoor area. The experimental results are shown in the figure. It can be seen that the visual SLAM of the two robots runs smoothly at the same time, and the right image is the process of their real-time map fusion. To further check if the system works, we did a comparison test between the system without cloud and the system with cloud. Results showed both systems can meet the basic real-time needs, but there was a difference in how well they worked. The system without cloud, when in adaptive mode, can only keep a simulation frame rate of about 20 FPS. The system with cloud runs stably at over 60 FPS because the local memory isn't big enough. The system without cloud ran out of memory during 3 separate checks. This happened when it had 1100 keyframes and made the process stop working abnormally. On the other hand, the system with cloud can finish the mapping task successfully, and the number of keyframes steadily adds up over 2,500. Our successful test results prove that our method works. You can see from these operation charts that the system can do localization and mapping well. Most importantly, results show that compared with the traditional or BSLAM3 framework, our cloud-based architecture makes pose estimation more stable and improves how well maps are combined. Also, it cuts down a lot on the need for computing resources and edge devices, and this was one of our main points at the start. Part 4, summarize the above content. To sum up, this research introduces a collaborative plan based on cloud-native architecture. It's used to solve key problems of computing power and real-time performance in traditional visual SLAM systems. By building an edge cloud heterogeneous computing model, we've successfully divided multi-agent SLAM tasks into layers and scheduled them dynamically. The engineering value of this work is that it provides a scalable, lightweight SLAM solution for mobile platforms like UIIP's ground reconnaissance robots. By using the power of cloud computing, edge devices can focus on collecting data and carrying out tasks. This makes them more flexible to use in important mission scenarios like battlefield reconnaissance and disaster response. Thank you for listening to our presentation.
Okay, thanks for your report. It's very excellent. Now, any questions for this report? Okay, now, due to time limit, we will move on to the last report titled Demonstration Method for DDMA Memo in Strong Clutter Background by Li Jun. Hi, Li Jun, you can start your report now.
Okay, thank you.
Good morning, everyone. My name is Li Jun. Today, my topic is about a demodulation method for DDMA memo in strong clutter background. My presentation is divided into Good morning, everyone. My name is Li Jun. Today, my topic is about a demodulation method for DDMA memo in strong clutter background. My presentation is divided into the following 4 sections. First, I will begin with an introduction to the research background. MIMO millimeter wave radar has been widely used in automotive and UAV scenarios. Doppler division multiplex size modulation ensures wave orthogonality through Doppler phase coding, which is central to MIMO radar. This work focuses on demodulation method for DDMA MIMO radar. In this section, the fundamental principles of DDMA and the proposed methods will be introduced. As indicated by the formula on the left, uniform phase DDMA applies phase modulation across pulses from different transmit antennas. As shown in the figure on the right, the immediate frequency signal's range Doppler spectrum is divided into many subbands along the Doppler dimension. In this figure, signals from each transmit antenna cyclically shifted into a separate subband to ensure orthogonality. The DDMA modulation creates Doppler ghost peaks and inserts empty subbands that hold no target peaks. To demodulation correctly, the system must pick out the signal spectrum that is not phase coed. Only then can it estimate the target's true velocity. In our research work, this demodulation process first applies FFT and winter filtering to the immediate frequency signals. Then, the background counter suppression method is performed by averaging multipolarity spectrum to estimate and subtract counter, effectively highlighting the target spectral peaks. Next, target peaks are extracted from the north RD spectrum and created by the peak correction method. This method sorts subbands by power and sets an adaptive threshold to label subbands as 0 and 1. Then, accurate DDMA demodulation is realized according to the rising edge characteristics of the corrected date. Finally, CFAR detection is applied for parameter estimation. In this section, the experimental results of the proposed methods will be presented. This table gives the system parameter settings. Experimental scenarios include vehicular and UAV scenarios. Taking the processing results of 6048 frames from the vehicular scenarios as an example. Figure A and B present the RD map of the immediate frequency signal before and after denoising by the background counter suppression method. The results indicate effective counter suppression and enhance the possibility of target spectral peaks. Figure A and B compare the detection results before and after peak correction method. In this case, peak loss occurs at the 19 and 25 TH subbands, which severely distributes conventional detection method. After applying the method, the target velocity is successfully demodulated, demonstrating the effectiveness of the peak correction method. In the vehicular scenarios, 19 frames of data were processed. The left and right figures give the accurate target range and velocity estimation of 60 frames of signal, respectively. Moreover, the left and right figures give two sets of experimental results in the UAV scenarios. The experimental results from the UAV scenarios confirm the effectiveness and the reliability of the proposed methods. In the last section, the conclusions of this research work will be summarized. Here is a brief summary. This paper presents a counter-resistant DDMA memory data solution, introducing a background counter suppression method and a peak correction method. These methods effectively address subband power distribution issues in high counter environments. The experimental results demonstrate the broad applicability of the proposed method across diverse experimental conditions. The above is all about our research work. Thank you for your time.
Okay, thanks for your report. Any questions for the last report? None. Okay. Okay, due to time limit, now it's time to end this session. Thanks again for all the reporters.
Thank you, Mr. Chairman. It's a nice and very productive session. Well, unfortunately, a little bit out of time, but still. So now we have lunch, but during the lunch will be also online ceremony for target recognition hackathon. So you may grab a snack and well, find something interesting news about what is going on in this field, because I guess the ceremony will be online. Am I right? Yes? Yes, okay. So now, so I think, so when should we start? I mean, the ceremony?
Okay, sure.
When? Let's decide, because actually, so we have just 1 hour, just half an hour to have a rest, and during this time we...
Maybe
10 minutes?
5 minutes later, yeah.
Okay, let's just grab a snack, and in 5 minutes on the screen will be a ceremony and some presentations for the winners of the hackathon challenge, ATR challenge. Thank you, participants.
Thank you.
丽姐呢？她叫来拍照呀，人呢？
Сейчас у нас сам. О, есть. Центрально можешь дать?
Okay, it's okay. Yeah.
Okay?
Okay, yeah. Yeah.
All this.
你们就看，你们能切到那个哪方向吗？可以这样。
哦。
啊，这个已经有了吗？看里面有了，分画面里面有了这现场的画面。
Сейчас, просто вообще плавно, я сейчас пока плавно.
可以了是吧？可以是吧？
这是这边是这是的。
It's okay?
Okay, yeah, yeah.
Все, оставляем это.
Perfect.
Ага, все, тогда спасибо. Добрый день. Так, давайте, пожалуйста, через минут 10. У нас может сейчас церемония будет, хорошо? И после минут.
Ну, то есть там будет момент перед
сессией. Как на обед там.
Все, вы хорошо.
Да, подойдете, все сделаем. Спасибо. Вот это именно вот это. А, все, супер, окей. Nice.
Okay, fine.
Hi everyone, thanks for being here to in the ATR Challenge Award ceremony. I'm glad to be the host of this ceremony. In this year, our ATR Challenge have 2 tracks, and the whole challenge was promoted with the PRIP conference. Yeah. After several months intense competition, several teams have been the winners for the ATR Challenge. Today we are honored to invite one of the winning teams from Belarusian State University of Informatics and Radiomatics to be here. Now let's welcome the winning teams on the stage. Okay. Congratulations to all of you. Here is the certificate and the trophy. Okay. Can you share a few words with us?
Yes. I want to say a special thank you for the organizers for the event, for the wonderful people here, and a great ceremony. Thank you.
Okay. Thank you for your inspiring words. Okay. Now we suggest we give a second round of applause to the winning team. Okay. Thank you. Okay. In the following part, we will present several of the winning solutions of 4 winning teams in the big screen. Sorry, wait a moment. Okay. Okay, here is the winning solutions for the first winning team. Okay, you can start the video.
Yeah. We also present the result of our work in 2 key areas. We will begin with the second track, which is dedicated to the case of object detection in complex visual scenarios. We have identified 3 primary types of CMS that present the greatest difficulty. Low light and nighttime conditions, characterized by strong reflections and haze, which lead to missed detections and low model confidence. Dense sparkling, lots and facial occlusions, as well as motion blur, which cause errors in boundary definition and classification, for instance, between cars and trucks. Finally, small and distant objects, which, when viewed from a wide angle, result in significant localization errors. To address these challenges, we are introducing a progressive training strategy for the UIIP size model, based on the phased enhancement of HSV augmentation. By using weights pre-trained on the control dataset, we sequentially adjust the parameters of all transformations. This approach significantly increases the model's robustness in detecting small objects and in nighttime scenarios with low resolution, allowing us to achieve a MAP 50 score of over 0.75 on our test set. The training process is structured as a three-phase pipeline. Phase first, 2000 average. We start with standard hyperparameters. This allows the network to quickly adapt to our data distribution by leveraging the future extraction capabilities of the pre-trained model. In this phase, the model learns the basic features of objects in the original color space. Phase second, 2000 average. At this stage, we increase the intensity of color perturbations. This forces the model to recognize objects under significant variations in brightness, saturation, and hue, preventing overfitting to specific lighting conditions. Phase 3. We then reduce the augmentation intensity to 0.6. This phase refines the model's generalization ability. By working with moderate color perturbations, the network learns to extract deeper, more robust features, ensuring stable performance across device environments. In summary, our system strategy effectively leverages the advantages of pre-trained weights and systematically adapts the model to challenging conditions, achieving high generalization capability. Let's process to the results. The graph, figure 1, illustrates the dynamics of K metrics on the validation set. We observe a confident increase to precision from 0.34 to 0.79 and recall to 0.71. The primary quality metric, MAP50, stabilized at a level of 0.75 and 0.76. Consequently, the loss function decreased monotonically, which, together with a smooth and decaying learning rate, indicates that the model has reached stable convergence without signs of overfitting. Our analysis of the dataset, figure 2, related two key characteristics. First, a pronounced long-tailed cost distribution. The number of common like cars and trucks significantly exist that of rare classes, such as industrial vehicles. Second, the majority of objects in the image are small, which is typical for detection tasks in dense environments. These observations form the basis for our choice of the lightweight UIIP size architecture combined with a proposed augmentation strategy, which specifically targets the improvement of small and rare object detection. On this slide, you can see clear examples of our model's performance after the completion of the third training phase. The results demonstrate high effectiveness in the target complex scenarios. The developed solution holds significant potential for application in areas such as urban traffic monitoring, drone-based security, and logistics management in industrial parks and campuses. Now let's move to the first track. Here we propose a hybrid solution that combines two approaches: fast candidate filtering using UIIP and precise local feature matching using LFTA. This choice is driven by the strengths of each method. UIIP is distinguished by its high operational speed, which allows for the efficient filtering of obvious matches, and narrowing the search area LFTA in turn provides high accuracy in matching dense feature spaces, which is critical for determining the precise location and transformation of an object. The workflow is as follows. fast filtering, the UIIP model processes the image and selects candidates with a confidence score above 0.1. Precise matching, the remaining more complex cases are passed to LFTR for detailed analysis, and finally finalization. The results from both models are combined to form the final output. Currently, the positioning accuracy IOU and valid samples has reached a practical level. However, we see potential for future improvement overall performance, especially under conditions of significant changes in viewpoint and scale. Here we demonstrate two illustrative examples. The first shows the results of the UIIP model on a high confidence object. The second showcases a complex case where LFTR successfully matched object despite a significant perspective shift. The hybrid approach is particularly relevant for tasks in remote sensing, reconnaissance, and change detection. Its key value lies in reducing costs associated with data annotation and model training, as well as enabling rapid adaptation to new types of targets. For deployment, we envision using a lightweight version of UIIP and distilled or pruned LFTR model on edge devices. Thank you for your attention. We are now ready to answer your questions.
Okay, this is a winning solution from the international team. Now we have three other winning solutions from China. Let's go move on to the second winning solution.
Hello, everyone.
Yeah, you can start your video now.
We are Team Fusion 2025 from School of Automation, Hangzhou Dianzi University. We won the second prize of the ATR 2025 competition. Task 1, cross-modal visual prompt-based object matching and recognition. For track 1, we reframed cross-modal object detection based on visual prompt as an image registration task and designed a dynamic switching framework for cross-modal image registration to meet the requirements of both detection accuracy and real-time performance. The architecture of Minima is adopted to serve cross-modal challenges. After estimating the geometric transformation between images, we can map an object's location from a prompt image to the target image. To balance real-time performance and detection accuracy, our system dynamically switches between superpoint plus light rule and Roman based on the number of the inliers. In Minima framework, generative models are used to create large-scale cross-modal datasets to train a deep learning model that can handle modality differences. A two-stage training procedure is adopted for training. The matching model is first trained on the original dataset to learn geometric relationships, and then fine-tuned on the generated cross-modal dataset to make its features robust to modality differences, enabling stable cross-modal matching. We use superpoint plus light glue as our real-time matching algorithm. Superpoint is a network to extract key points and descriptors from an image. It has one encoder and two decoders. The encoder processes the image to extract core features, which are then used by the key point decoder to output a key point probability map, and by the descriptor decoder to generate dense descriptors for matching. Light glue uses a multi-layer network with self-attention and cross-attention to refine these descriptors and find future correspondences between two images. It employs an early exit strategy to speed up the matching process by only performing deeper computations on uncertain points. The final matches are determined based on the similarity and matchability scores of the remaining points. As a highly robust matching algorithm, Roman adopts pre-trained genome V2 features to build a high-precision future pyramid. Its unique transformer decoder is designed to predict uncode probabilities, which effectively solves the difficult one-to-multiple matching problem in cross-modal images. Two matching strategies are compared through experiments. Superpoint plus light glue scored 3.5783, and the switching strategy scored a significantly higher 4.6565. This shows that the strategy of fusing two models with different features can improve matching accuracy and overall performance. Task 2, optical detection and recognition of vehicles in UAV imagery. For track 2, vehicle detection from UAV-based visible image faces many challenges, including variations in category, viewpoint, and weather conditions. To address these, we propose a novel detection framework that integrates a powerful Next VIT backbone into the V8 architecture. We extended YOLO V8 by adding advanced data augmentation, such as copy-paste, optimizing network architecture, and supporting multimodal fusion detection and video detection. The framework also enables one-click training and testing for rapid deployment. To address vehicle detection problem, we adopt Next VIT as the backbone, which combines CNN-based local feature extraction with transformer-based global modeling. We further enhance the detection accuracy through a multimodal ensemble strategy that integrates outputs from models trained with different settings. Our innovations are threefold. 1. Extending YOLO V8 to support HBB, OBB, multimodal, and video detection. 2. Introducing Next VIT for efficient local global future learning. And 3. Boosting accuracy with a multimodal ensemble. The pipeline as follows. Next VIT extracts local and global features. A one-by-one convolution addresses channels, and the YOLO V8 NAC uses features into multi-scale maps. The decoupled head separately predicts position, category, and confidence. Training adopts task alignment only, with multitask loss, and non-maximum suppression is applied during post-processing. We selected Next VIT as backbone because it effectively captures both local and global dependencies. Together with FPN for semantic propagation, PAN for detail enhancement, and the decoupled head for separate classification and localization, the network is able to handle both large and small object detection. For the computation, we focused on improving robustness through model ensemble. Specifically, we trained 3 models. 1. Next VIT with YOLO V8 head, trained for 100 pokes. 2. Next VIT with YOLO V8 head, trained for 200 pokes. 3. Next VIT with a custom head inspired by YOLO X, trained for 100 pokes. Our network configurations used in the computation are presented as follows, highlighting the next VIT backbone and the different detection heads employed in our experiments. We then integrated these predictions using non-maximum suppression. This NMS-based ensemble significantly boosted performance, achieving a competitive score of 34.59. Detection results further confirm that our method is robust across skills, scenarios, and weather conditions. In summary, our next VIT UIIP framework demonstrates strong robustness to occlusion, voltages, and challenging conditions. Future work will explore multimodal fusion detection for extreme weather. Thanks.
Good morning. Distinguished guests, it is my honor to represent the team system-led prediction vanguards motivated by the XR challenge in the PRIP'2025 theme. We address task connected one with the topic efficient cross-modal matching and retrieval around multi-sphere enhancement. We identify 4 critical challenges. 1. Large modality gap between SAR and view images. 2. Extreme viewpoint variation. 3. Dramatic scale diversity, many oversized samples. 4. Noisy correspondences that propagate localization error. Overcoming these bottlenecks is essential for top-tier performance. Our 4-pronged remedy 1 light glue to mine context-aware domain invariant descriptors. 2. Rotation invariant dog detector plus hardnet descriptor for robust key points. 3. Multi-scale operator that learns scale-specific evolution for least square solver to estimate the optimal homograph Y and suppress misalignment. Inside light glue, Pagdog hardnet as the feature extractor and code matches via confidence-based weighting, yielding a lightweight yet expressive model. For coordinate transfer, we will screen key points, release squares, refinement, mean projection error, and back project target locations via the perspective matrix. The full pipeline is summarized here. Adaptive prescaling, cross-modal key point extraction, context-aware matching, and localized TIR module. Qualitative results across scenarios, confirm accurate registration and precise geolocalization. Innovations. First, preprocessing plus generally stable key point extraction. Second, joint uptime inside TIR for high-quality matching. Finally, least squares coordinate, transform guaranteeing robust positioning. For task native to represent UAV data and detector tailored for complex urban UAV imagery, targeting small object omission, scale variance and illumination disturbance. UAV data introduces 3 core designs, full source augmentation, frequency spatial fusion, and geometric adaptive calibration, delivering strong operational potential. The end-to-end architecture fuses frequency and spatial streams while maintaining real-time speed on embedded UAV boards. To rescue tiny objects, the MSF-FFT module performs FFT enhancement in the frequency domain, FFT reconstruction and gated weighting, preserving high-frequency cues at 0 extra cost, complementary modules, frequency-aware downsampling, and semantic alignment calibration, stack further harmony at crossview, multi-scale features. We boost the generalized set ion via large-scale mixed-city training on drone vehicle and ATRU model, covering extreme illumination, inclusion, and scale. The redesign loss at UPS 1.25 box, extension plus ESI reconstraints, accelerating convergence and tightening localized TIR. Extensive experiments showed UAV data tops public UAV benchmarks, especially on small instance subsets. Ablation studies verify each component's contribution. UAV Delta R operates around the clock, on terrain and full view, ready for reconnaissance, anti-terror, patrol, and smart traffic. The same variant runs 30 FPS on board, cutting response latency dramatically. In summary, UAV Delta R advances data augmentation, feature fusion, cross-design and geometric calibration, jointly elevating detection, stability, and accuracy in crowded cities.
Okay, thanks for the winning solution. Let's move on to the last solution. There's no sound in Changsha, in China. Hi there in Changsha, can you hear me? There's no sound from your side.
Yes, I'm sorry, but the last one has no voice. But so I think it's so.
Okay.
That's all. I'm sorry.
Okay, it's fine. Okay. Thanks for all the winning solutions by the participants. I'd like to thank the PRIP conference for joint promoting our ATR challenge, and we also like to thank the sponsors, volunteers, and anyone who has contributed to this ATR challenge event. And we hope more people can participate in the ATR challenge 2026 next year. Thank you. Thanks for your attention. Now, sorry, wait a moment, and we will start the next session, maybe 2 minutes later. everyone, and now it's time for the next session. I'd like to introduce the session chairman, Marina Luksevicki from Belarusian State University. He will handle the next session. Okay.
Thank you. Thank you very much. Thank you, dear guests, dear colleagues, and let's start our session. Yes. And who will be the first? Puchovskaya Polina. Yeah, Polina. Polina, give 2 minutes for us. Yes, for preparation. Yes. Puchovskaya Polina, localization methods of scattering inhomogeneities in acoustic imaging. Acoustic imaging. Mm-hmm. We need some minutes for uploading presentations for our presenters. That is why we need to wait. I apologize for the delay. Yes, Polina, have the floor, please. Let's start. Yes. Please.
Hello, everyone. My name is Polina. The theme of my talk is localization method of scattering inhomogeneities in acoustic imaging. The questions of mathematical modeling of sound propagation in fluctuating marine environments have attracted the attention of specialists in various fields of science and technology for many years. This study continues the investigation of the inverse problem for the non-stationary radiation transfer equation, which involves determining the scattering coefficient discontinuity surfaces based on the time angular distribution of the sound to the equation at a given point in three-dimensional space. The process of propagation of acoustic waves is described by the radiation transfer equation. In an isotropically scattering medium, this equation has the form 1, where the function I is interrupted as the energy flux density of the wave at time t at point R propagating in the direction k, with the speed of sound in the medium c, mu and sigma as the attenuation and scattering coefficient respectively, j as the sources of the sound field in the medium. We supplement equation 1 with the initial condition 2. We will assume that the function j describes a point source of radiation concentrated at the origin of coordinates and emit a pulse of unit power at a time t equal to 0, its relation 3. Let me formulate the direct and inverse problem for the non-stationary radiation transfer equation 1. The problem of determining the function I from equation 1 and initial condition 2 with given parameters c, mu, sigma, and j is the direct problem. In this paper, it's assumed that c is a scalar quantity and sigma of r and mu the piecewise constant functions in three-dimensional space with sigma I being less than equal to mu. The inverse problem is the problem of determining the discontinuity surfaces of the function sigma from relation 1 to 3 and additional condition for if t and p are known. To study the inverse problem, we need to establish some properties of the direct problem. Therefore, let us first consider the direct problem. The solution of the direct problem can be found in the form of Newman series, where the function in are defined recurrently fixed. Since the radiation source is represented in the form 3, the component I0 of the Newman series 7 is the singular part of the solution of the radiation transfer equation, and the remaining terms of the series as the regular part. By carrying out some transformation, we can obtain a solution for the flux density of the single scattering radiation. That is, the function I1 at the point I0 can be calculated using formula 8. For such k and t, relation 8 can be rewritten as 9. From where we find the desired function sigma, relation 10 gives the solution to the inverse problem of the single scattering flux density, the speed of sound, and the attenuation coefficient are known. Moreover, using the formula, we can find not only the discontinuity surfaces sigma, but also the function itself. In practice, as in the formulation of the inverse problem under consideration, the total radiation flux at the point I0 is considered to be known. Therefore, finding the function sigma using formula 11 leads to the expected error of a single approximation. In this connection, the formulation of the problem of finding only discontinuities of the function sigma arises. For the numerical localization of the discontinuity lines, gamma in these studies, an indicator function is used, which is a different analog of the gradient modulus with respect to the variable r from the expression contained in the left-hand side of equation 11. Introduce a jump function s with respect to the variable t expression 12. Under the condition of generalized convexity, the function 13 is continuous with respect to the variables t and k. This leads to the conclusion that the discontinuities of the function p(kt) are completely determined by the discontinuity of the function sigma. Thus, the indicator functions takes non-zero values at points r belonging gamma. Let us consider the function p, which is known a discrete set of points. In this case, the numerical implementation of the proposed algorithm for localizing the discontinuity lines of the function sigma in plane 14 can be performed, for example, using the function 13. As the discretization step approaches zero, the indicator function takes non-zero values in some small neighborhood of the surface gamma. In relation 15, linear interpolation with respect to the variable p was used for the function s. The sounding data synthesized using the Monte Carlo method correspond to the technical characteristics of the multi-beam sonar. The sonar operates is in 3 scanning modes with an effective horizontal beam of 3 degrees, 1.5 and 0.75 degrees, and a number of beams of the 120, 240, 480 on circle. The algorithm was tested on a digital phantom simulating a marine environment containing spherical inclusions with slightly different scattering and attenuation coefficient. The speed of sound and the attenuation coefficient correspond to real values characteristic of acoustic sounding in a marine environment at a frequency of 260 kilohertz. Figure 2 presents the result of reconstructing the discontinuity lines of the scattering coefficient using the homogeneity indicator. This corresponds to 3 scanning modes of the circular sonar with m equal to 240, 120, and 60 respectively. As expected, the quality of the reconstruction deteriorated was a decrease in m for the given algorithm for reconstructing the discontinuity lines. However, even at m equal to 60, the analysis of the obtained images the location of the desired inhomogeneities. The reconstruction using the indicator has one drawback associated with the partial loss of reconstruction quality near the point where the beam originating from the origin touches the discontinuity line of the scattering coefficient. The result of the simulating modeling demonstrated that the proposed tomographic algorithm can be effectively used for the localization of inhomogeneities in relatively small water bodies with the application of modern multi-beam sonar, provided that the scanning mode is appropriately selected based on the size of the investigated inclusions. This highlights the potential of the algorithm for partial application in underwater acoustics, particularly in scenarios where accurate characterization of the medium is essential. Thank you for your attention.
Thank you, Polina. Please, questions. We have time for one question.
I have a small question. Thank you very much. But in your example here, you have a source of acoustic data, right?
Yes.
And where is the receivers? What kind of information you use for reconstructing boundaries?
Mm-hmm.
Where are the receivers?
We synthesized data using Monte Carlo method in direct problem. And then we make inverse problem.
It's something like magic. You have a source information which provides some acoustic data. Then you measure some I don't know, amplitude of the signal or something. Where you measure it?
Amplitude? No.
No.
We have point source.
Point source.
Impulse point source.
Yeah. And based on this impulse point source, you just reconstruct the boundaries of all objects of this.
Yes, we make data myself.
Yeah, but you should measure something based on the source information and then reconstruct the boundaries, right? So you measure something.
What is measure?
Measure, I mean, измеряете.
А.
Какую-то информацию вы измеряете где-то, на основе которой вы потом устанавливаете границы сцены, нет?
No.
Не совсем понимаю, как это вам удается. Спасибо. Thank you very much.
Thank you, Polina. Thank you. And the next report will be from Safiullin Tulibai. Yes. Calculating high frequency consumer price sub-indexes, web scraping and classification. The second.
Good afternoon, everyone. Thank you for being here. My name is Tulibai Safiullin, and today I'm exciting to present our joint work with the National Bank of the Republic of Belarus. And this work focusing on calculating high-frequency consumer price sub-indexes. This version presents only the first two phases of the study, web scraping and classification. We all know that timely economic data is lifeblood of effective policy and business decisions. However, official statistics like the consumer price indexes often come with significant publication lag. This creates a critical need for alternative high-frequency data. We can find such data in online. The digital footprint of retail is vast, updated daily, and incredibly detailed. Previous studies have shown a stable correlation between online and offline prices, making web data a powerful tool for building early warning indicators of inflation. The challenge, however, lies in taming this data, automating the collection, and most importantly, making sense of it, which is exactly what our project set out to do. Our goal was to develop a fully automated pipeline to collect online price data in Belarus and accurately classify thousands of products into official statistical categories using machine learning. So we built a robust ETL system in Python to scrape two major Belarusian online grocery platforms. We used a combination of tools, Request and Beautiful Soap for standard websites, and Selenium for platforms with dynamic and JavaScript heavy content. This wasn't without its challenges. We have to solve problems like broken links, unstable website structures, and inconsistent discount formatting. We implemented solutions like exponential backoffs for retries and redundant checks to ensure data integrity. The results was a reliable pipeline that collects over 33,000 product records with weekly updates, forming a solid foundation for our analysis. Raw scraped data is messy. Our first step was a strict cleaning process, removing items with missing prices, deduplicating products listed in multiple categories, and filtering out non-representative items like seasonal goods. The core challenge was categorization. A store might call categories as they want, but we need to map it to the precise official classification from Belarus National Statistical Committee. Our solution was a hybrid approach, first an automatic mapping using text similarity algorithms, then a manual dictionary for clear matches, and finally a rule-based system for ambiguous cases. This gives us two clean, labeled datasets from our two sources ready for machine learning. A key issue we identified here was a significant imbalance in the categories. Some categories had thousands of products, while others had very few. This meant we had to choose evaluation metrics, wisely focusing on the F1 score and the ROC score, which the robust to such imbalance. Now, for the machine learning, we tested 5 different algorithms from logistic regression and SVM to random forest and gradient boosting under 2 case scenarios. First, we used the combination of the product name and the shops category as input. Second way is more ambitiously. We used only the product name. This second scenario is crucial for creating a universal classifier that can work on any website, even if its category structure is completely different. All text was converted into numerical features using TF IDF vectorization, and we performed careful hyperparameters tuning for each model to ensure a fair comparison. The results were highly encouraging. When using both the name and shop category, all models performed exceptionally well, with ROC scores exceeding 0.99. The support vector machine and our ensemble model delivered the most balanced performance, but the real test was universal classifier using only the product name. Performance remained very high, with F1 scores above 0.85. Again, SVM and the ensemble lead the way. This proves that a cross-platform solution is not just a theory. Most importantly, when we validated our best models on data from the second website, data they had never seen before, they maintained this stellar performance with ROC score still above 0.99. This demonstrates the model's ability to generalize beyond the initial training data. To conclude, we have shown that the combination of web scraping and machine learning it's not only feasible, but highly effective for automating and classification of consumer goods in Belarus. We have developed a robust data pipeline and identified optimal models with SVM and ensemble methods performing best. Crucially, we have proven that universal classifier is viable. So what's next? This classification engine is the key to the next stage. The actual calculation of high-frequency consumer price sub-index, and this will allow for the creation of a real-time inflation monitoring system, providing policy makers and businesses with vital and timely tool for economic assessment. Thank you for your attention.
Okay. Thank you very much. I have two questions. The first question is about imbalanced classification problems. Yes, you mentioned that you had imbalanced data set. Yes, did you use some specific techniques for working with imbalanced data? For example, it is possible to use imbalanced learning library. Yes, Python library.
Yeah.
And did you try to use it?
No, because of high effectiveness of our algorithms of classification, and it's not necessary, I think.
Okay. And the next question about metrics. You mentioned accuracy. Did you try to use the balanced accuracy? It's most suitable for imbalanced classification.
Balanced accuracy. No, I think F1, for example, it's balanced accuracy and seconds, accuracy and precision. I think it's effective for our question.
I suggest you to use it.
Okay.
Try it, please.
I'll
Okay.
try.
Thank you very much. The next report will be from Kim Tatiana. Please, Tatiana. Control of an anthropometrical working robot using reinforcement learning. Tatiana, please.
Good afternoon.
We have some problems with presentation. Just a minute, please. We will try to upload presentation.
Сейчас еще раз одну секунду. Сейчас попробуйте.
So today I want to pleasure my presence of control of anthropomorphic walking robot using reinforcement learning. So today, control complex humanoid robots with many degrees of freedoms remain a major challenge in robotics. Traditional control methods like a pin controller often struggle with dynamic environment and require pressure models. The goal was to explore whether reinforcement learning, or RL, could enable a robot to autonomously learn stable, energy efficient, and human-like working without explicit programming of motion patterns. They aimed to achieve a high degree of adaptability and coordination across all limbs through trial and error, guided only by reward signal. In reinforcement learning, there are agent, and its case as a robot controller interact with an environment by observe its state, taking action from environment and receive reward. The objective is to learn a policy that maximizes the cumulative future reward over time. Since I'm controlling joint control for continuous physical quantities, and I need an algorithm suite for continuous action space. I use DTPG algorithm, and it's used model free of policy RL algorithm, and it combines actor and critic. And this algorithm has two networks. It's named actor and critics. Where actor which out the best action given the current state, and critic evaluate how good that action or not. So in this slide you can see a full architecture of environment and RL algorithm, and our robot model was implemented in MATLAB Simulink for realistic 3D physics simulation because it can include gravity, friction, collision, and joint dynamics. The agent observes K state such as joint angles and velocity from action to block Newman, body orientation and linear velocity, foot contact sensors. For creation a good action, we need to normalize torque command, and it's ranging from -1 to 1 for each joint. And then inside of block Newman, it transformed to physical valid torques from stiffness, dampening, and position limit. In this table, before start training, every joint saturated from degree, and this setup allows us to simulate real world. Contains while training a policy that can potentially be transferred to hardware. The second table is parameters for the GPG agent for take a good result. The second, I think it's a main point. It's a create reward function because it's a main guide for learning. And it shapes the desired behavior, and you can see a formula where use plus B. It's a primary goal where reward for speed, and minus P it's a penalty for deviation from the straight path. Minus Z it's a large penalty for falling. and minus z, x, it's penalty for high torque, prompt energy efficient. And t, it's bonus for episode duration, prevent cheating for falling forward quickly. So it gets for after several trainings. Full training time gets more than 9 hours, more than 9 hours, yeah. And in this figure, you can, it's a traditional figure of reinforcement learning, and the blue line shows raw episode reward, highly variable typical in array, and the red line, it's moving average. It shows a clear upward trend. The green line is critics estimate of initial state value, so also increasing, meaning that agent is learning better long-term prediction. It's a result of how joint move, how moved one leg, left leg, and after training, the robot exhibits stable, smooth, and coordinated forward locomotion, and you can see joint torque signals during walking. They are periodic, synchronized, and show clearly left, in this figure, left moves, characteristic of natural bipedal gait. Can you show the other presentation? And now I want to show a short another presentation where I show how robot learn. So it's one side you see a physical robot, and the left side it's a model of humanoid robot. And this before training, I programmed every joint of robot and how robot should move. Without using any algorithm. So next, when I prepare all all information and environment for training, robots start learning. And first, its step was not normal, and so he tried to move forward, but after several meters he falling. So it's take maybe 1 hour. After maybe 3 or 4 hours, he tried to move forward without. He tried to imitate a work or a human walking, and you can see it's follow reward function, because he tried to forward, he don't falling, and he try forward during all simulation time. This is a final video where after training I run without any without reinforcement learning, just actor, and he, I think, learned to imitate human walking. Thank you for attention, and if you have a question, I'm happy to answer.
Questions, please? I have a question. May I ask? Okay. First of all, reinforcement learning is a very difficult topic.
Yeah,
Yes,
I'm
it's a
agree.
framework of machine learning. Yes, and yes, reinforcement learning is a very difficult topic. And why did you use MATLAB? And why you have such high training time? Did you use GPU for training?
I use MATLAB because there I can create an environment from zero. So I know that in Python, Gym, it has ready environment, ready robots. It's easy, and it's if I created it without any science results. Why it's MATLAB? Because I can notice all results, all data, and control every process when during agent learn. I use GPU and parallel learning. That's why it takes 9 hours. Because before the final result, I use just without parallel, and it takes more than 20 hours, maybe 24 hours.
Okay, thank you. Did you try NVIDIA Omniverse platform for reinforcement learning? Yes?
Yeah.
Is it okay for you, for your task?
NVIDIA GeForce, maybe P2000, and nowadays it's not enough for me.
Okay, thank you. Thank you.
Thank you.
The next presentation will be from Ivanuk Alexander and Burko Liana. Burko Liana will present a report on clonable identification and true random number generation based on PRIP. Please.
Hello. Hello, my name is Liana Burko and I'm from Belarusian State University of Informatics and Radioelectronics. The topic of my current research is unclonable identification and true random number generation based on CIO-PUF. Security is paramount in nowadays interconnected world, and innovative solutions are constantly evolving. Robust methods of protection are highly desirable for sensitive data and systems. Physical unclonable functions, PUFs, offer a unique approach to security. Their unpredictable nature makes them incredibly difficult to clone or replicate, because fake and manipulated PUFs are not able to generate the true IDs. This technology has great potential for improving security in various applications, as it has a simple structure and is capable of solving two problems at the same time. According to various threat sounds or jitters caused by various factors, which include instability of the supply voltage, thermal loss of the environment and the semiconductor devices, imperfection of the measurement equipment, and etc., PUF circuits can also, in addition to identification, solve the problem of generating true random numbers. PUFs are a technique in hardware security that exploits inherent device variations to produce an unclonable, unique device response to a given input. Generally, a PUF's performance is measured by its level of robustness, uniqueness, ease of evaluation, difficulty to replicate, and difficulty to predict or randomness. There are many types of PUFs, they are on the screen, and in our investigation we used three-installator PUF. The classic raw PUF design compares pairs of installators, and it requires a complex selection scheme that often produces biased results across different FPGAs because of differences in routing and placement. On real silicon or ASICs, small deviations between installators create uniqueness, but in FPGAs, the differences are dominated by routing and produces predictable outcomes. To overcome this, the approach is simplified. Instead of pairwise comparison, a single configurable ring oscillator is measured under different configurations. Each configuration produces a frequency value within a narrow range, and these values form multi-bit responses, and this method reduces hardware complexity and ensures uniqueness. In our research, this is a reduced circuit scheme of the CAO PUF for the counter. PUF generates an output bit sequence as a response to an input or challenge. Depending on the task, based on these answers, we can get either an identifier or true random numbers. The number of clock signals in a set time window is used as a quantitative measure. As a result, we have 31 data sets with different input in. The values from counter are integers, so every data set has 1,000 integer values. When converting the values into binary form, the division between stable and unstable paths is visible. The registered values in repeated measurements can be represented by the probability of the appearance of a single symbol in each digit of the counter. During the experiments, it was revealed, as can be seen in figure, that the values of all significant digits can be divided into 3 groups or subsets. The first one is the group of stable digits. On the screen is black or G0, which includes digits for which PG is equal to 1, and these values can be indeed used as identifiers. The next group of highly unstable digits, it is Y or G2. The probability of appearing 0 or 1 is very close to 0.5. This group can be used as a source of random numbers. And the last one, the group of conditionally stable digits, red G1. By various manipulations, this group can be brought to either a completely stable group or highly unstable group. In this research, we use the maximum likelihood method and expanded the identifiers with conditionally stable group. During the experiment, it was hypothesized that the data from CAO PUF counter form a normal discrete distribution. To test the hypothesis of normality, there are graphical and statistical tests. We plotted the distribution diagrams and verified that the values indeed satisfy the normal distribution. The QQ test shows deviation at the ends, and all data sets under study passed visual tests. Since the data has similarities with the normal distribution, there is need to construct a mathematical model of the ideal normal distribution to predict theoretically the functionality of the selected CAO PUF with known mean and variance. There is need to make sure that the bitwise probabilities of model data and of experimental data will be almost the same. To confirm this hypothesis, a software mathematical model of the CAO PUF scheme with a counter was built based on the NumPy library of the Python language, which generates a discrete set of a given size with fixed values of the mean and variance. Model is based on NP random normal function with routing to the nearest integer. We estimate the deviation between model and experimental PUF data using the normalized Euclidean distance between their vectors, which is less than 0.09, which shows sufficient level of similarity. On the screen is comparison with groups of model and PUF data for different key factors. Both real data and model mathematical data show a division into 3 groups. The sizes of these groups are almost the same. As a result of the research, we can suggest 2 estimations of the unstable part. According to this, it will be possible to estimate the size of the stable part and then build an identifier. The first one can be estimated with metrics based on minimum and maximum values. The second based on property of normal distribution. In theoretical normal distribution, 99.7% values are in range of 6 sigmas. But as PUF distribution has deviation at the end, as it was shown in QQ test, this matrix is more accurate than previous one. So the size of group G2 can be estimated with underlying expression from the screen. Another experimental results are illustrated with data sets from 4 similar FPGAs, with 4 similar CAO PUFs. All 4 FPGAs were initialized with the same bit image. On the screen, there is heat map of probability values from 16 combinations. It was shown that the counter values can indeed be divided into 3 groups, and the bits of the stable groups G0 and G1 can be used as identifiers, and G2 as a source of random numbers. The hypothesis is that all identifiers will be different. As it's shown in figure, sizes of G0 and G1 are different for all instances, and G2 is almost the same. According to the maximum likelihood mass estimation, we can breed the red group to the closest value. As can be seen in the right figure, red group has gone. Now there are only 2 groups, stable and highly unstable. The first one can be used for identification, and the second one for generating random numbers. Like in many articles, the metrics most usually employed to evaluate PUF performance are based on the average Hamming distance. First identifier was built with length of 6. That's equal to the minimum pole sizes of G0 group between all observed sets. Results of intra and inter-uniqueness are in the first table. Here we can see a key advantage of geometric mean, and it is its immediate identification of identical values as observed in C0. In this case, the uniqueness is weak, since there are repeating examples. The length of fully stable group not enough for good uniqueness. So that's why next identifier was expanded up with values from G1 or red group, according to the maximum likelihood estimation from previous slide. The minimum size of G0 and G1 group was 12. It can be seen that identifiers are different and have good intra and inter-uniqueness. Also, there is set variant, and here the ID length based on the estimation method of highly unstable group with 6 sigmas. The metrics can help to draw a boundary between unstable and stable group. For example, in experiment, estimation metric is 12 and is equal to 23, so the identifier length is 11. This approach is much easier for realization, because without any checking of length groups, only with sigma, the ID length can be chosen. The scores are slightly lower than those for ID with size 12, but still satisfy the conditions of uniqueness and differences. CIO-PUF is a simple design that exploits the same hardware to generate true random number response and unique identifier without the need of changing it. During the research, we have suggested 2 estimations of a highly unstable group and also provided ways how to expand the unique identifier. It was shown that identifiers from CIO-PUF are indeed distinct and unique and have good intra and inter-uniqueness. Thank you for your attention.
Thank you, Liana. Please, questions?
Can you explain this identification number which you generated? How stable? How other, for example, condition of environment, for example, temperature, you use 20 degrees and then measure for the temperature 23 degrees. Your results are like the same or not?
When our device is working in some conditions, this result will be stable, because some temperature or something else will not affect this. So this amount of bits will be stable.
Thank you. Please, take a seat. Okay, the next report will be from Daria Zhalova, an automatic bird voice recognition system based on artificial intelligence technologies. Please, Daria.
My name is Zhalova Daria. I present to your attention the development of a neural network-based model for automated bird voice recognition. The model is designed to support scientists in monitoring forest bird species by providing accurate identification of vocalizations in audio recordings. The purpose of our project is to develop and evaluate a machine learning model for the automated recognition of bird vocalizations. Such a model can support long-term and seasonal monitoring of species diversity in natural habitats and ecosystems. To achieve this goal, we set several objectives. First, we focus on designing and training a neural network-based model capable of recognizing bird voice signals with high accuracy. Second, we work on preprocessing and accumulating annotated audio recordings in a structured database, combining both proprietary and publicly available sources. And third, we evaluate the recognition quality of the model across different bird species and under various acoustic conditions in order to confirm its applicability for biodiversity monitoring tasks. For the recognition of bird populations, the neural model was developed and trained capable of identifying 116 species of forest birds. For training purposes, ornithologists collected audio recording of bird songs using recording devices, as well as from the open database Xenocanto. To ensure more accurate training, each audio recording was supplemented by experts with annotations indicating bird species and timestamps marking the beginning and end of vocalization. As a result, the dataset comprises more than 3,000 annotated audio recordings and 56,500 annotations with a total duration of 76,000 seconds. To provide the model with properly formatted input data, the audio recordings were converted into ML spectrograms, which were then passed into a model based on an EfficientNet V3 architecture. To achieve robust recognition of bird populations, the audio recordings undergo several preprocessing steps before being passed to the model. First, we applied denoising techniques to suppress background noise and highlight the target signals. Then, to achieve robust recognition of bird populations, the continuous audio recordings are first segmented into 2 seconds windows. These windows are generated with overlaps, which both increase the effective size of the training dataset and serve as a form of data augmentation. Each 2-second windows is then processed to a compression and normalization, which ensures consistency across the recording with different amplitude and recording conditions. Finally, each processed segment is converted into a ML spectrogram, providing a 2-dimensional representation of the signal that is well suited for input into convolutional neural networks. In our study, the task of multi-label classification was selected for bird voice recognition. The choice is directly motivated by the nature of the data. In natural environments, several bird species often sing or call simultaneously, and these overlapping signals need to be captured by the model. It's important to distinguish this approach from multi-class classification. In a multi-class setting, each audio sample is assigned to exactly one category, making it suitable only when the assumption of mutual exclusivity holds. For bird populations, this would be highly restrictive since in many recordings more than one species is present. By contrast, multi-label classification allows each audio sample to be associated with several categories simultaneously. This makes it the most appropriate choice for our task, enabling the recognition of complex acoustic scenes where multiple species are active at the same time. Our model is based on the pre-trained efficient net B3 neural network, which we adapted to by removing its final classification layer. Since we work with bird vocalizations, the audio recordings are converted into MEL spectrograms, which are then treated as image-like inputs to a convolutional neural network. To adapt efficient net B3 for our task, we added several layers. First, a global average pooling layer, which compressed spatial information across feature maps. Next, we applied dropout, and finally, the model ends with a fully connected layer of 116 neurons with sigmoid activation for multi-label tasks, corresponding to the 116 bird species we aim to recognize. To evaluate the model, we used standard classification metrics, precision recall and F1 score. These metrics were calculated for each of the 116 bird species individually, and then summarized using different averaging methods to provide an overall performance picture. Fixed probability threshold of 0.8 was applied to interpret the model's predictions. This means that the model considers a species as present only if the output probability exceeds 0.8. Such a threshold allows us to minimize false positives and achieve more reliable recognition. For clarity, we present detailed results for the 10 best recognized species, while also reporting summary metrics across all species. The use of macro, weighted, and samples average provides a balanced view of the model's strengths and limitations, taking into account with both frequent and rare species in the dataset. And here you can see an example of automatic annotation from our model. And that's all.
Thank you, Daria. Questions, please?
Tell us, and your results here, classification results are K for single, right? Case when single voice.
Can you repeat, please?
I mean your table. You show the table. There are a class of birds, and these results are for single voice, right? Or you have a mixture of several voices, and you can recognize both, for example. You have a mixture of two birds at the same time.
Yes.
And what are your results of recognition?
Our model can recognize birds that sing at the same time, and these results for not the one recording, but its results made on the test dataset, yes. With bird vocalizations that can overlap.
So you mean that your model successfully works
Yes.
also when you have several voices at the same time?
Yes.
Yeah, okay.
Daria, I have a question about data labeling. As I understood, you used public data set, yes?
Not only. We use Xenocanta public dataset, but with using that dataset, we also not we, but ornithologists from another institutes collected recordings by themselves and then annotate them with bird labels that are presented there.
Did you use specific software for data annotation?
Ornithologists use Audacity for annotation. After labeling in this program, Audacity, you can download labels to your computer in a form of TXT files with timestamps of the beginning, end of vocalization, and the label of birds.
Thank you. Thank you.
Thank you.
Maxim Filipov will present theoretical study and experimental verification of recognition algorithms based on the measure of precedence. Please, Maxim.
One, two. Good afternoon. My name is Maxim Filipov, and I will present a report on the topic theoretical study and experimental verification of recognition algorithms based on the measure of precedence. The problem of object recognition is highly relevant now today. There exists a class of metric algorithms that can help address this issue. This study focuses on algorithms based on the measure of precedence, which relies on analyzing previous examples to make decisions in new situations. To apply recognition algorithms to practical tasks, experimental verification of their functionality is essential. Therefore, the development of a system capable of conducting comprehensive experiments is of undeniable interest from both theoretical and practical standpoints. I have already implemented a prototype of such a system and will demonstrate how it works later in the presentation. But first things first. Before solving the problem, we need to define it clearly. In this problem, we consider a set of objects divided into several non-overlapping classes. Within this set, there is a sample whose elements have known class membership. Our task is to classify the remaining objects in the set whose class membership is unknown. A general algorithm based on the measure of precedence consists of three key functions. First one, pairwise comparison function. This function evaluates the similarity between two objects within this set. The second one is class comparison function. This function assesses the similarity between an arbitrary object and each existing class. And the third one is decision rule. This function produces a binary vector whose length equals to the number of classes. Each element of the vector is set to 1 if the object belongs to the class corresponding to that index and 0 otherwise. To determine these three functions, some preliminary calculations are required. Specifically, we compute the center of each feature for every class, and then for each feature we calculate the distances between the class centers and the center of the entire set. Using these parameters, the functions described above can be defined as follows. The similarity function S takes values here. The similarity function takes values between 0 and 1. The closer the value is to 1, the more similar the compared objects are. The selection function F identifies the most similar objects from each class in the training set relative to the objects being classified. The decision rule assigns the objects to a specific class based on the outputs of the previous functions. A second variant of these functions can be constructed by inverting the corresponding functions from algorithm 1. So we just invert function s, 1 minus s from previous algorithm, and maximum functions we swap with minimum. In the third variant, we use the diameter of the set to define the functions. The first function is based on the similarity function s from the second algorithm, while the other two functions are analogous to those defined in algorithm 1. It is important to note that these algorithms can only operate on binary data. Therefore, before applying them, the data must be transformed using appropriate encoding methods. For categorical variables, one-hot encoding can be used, while quantitative variables can be encoded using binary encoding. To conduct experiments, several datasets with varying types of variables were selected. The employee dataset is designed for binary classification. It is imbalanced and contains only categorical variables. The heart disease prediction dataset is also intended for binary classification. It is also imbalanced, but consists primarily of quantitative variables. And the mobile price dataset, it is used for multi-class classification. It includes both categorical and quantitative variables and is perfectly balanced. All these datasets are relatively small, containing only a few hundred or a few thousand of objects. And they all were sourced from Kaggle. I tested all three metric algorithms mentioned earlier, along with several classical machine learning algorithms. The best performing results are highlighted for every dataset. So this is the employee dataset, heart disease, and mobile price. As we can see, at this stage of the research, the metric algorithms do not perform as well as the classical machine learning methods. Therefore, further experiments involving different combinations of comparison functions and decision rules are necessary. They may improve the accuracy of the algorithms for specific problem sets. To conclude, I would like to present a brief showcase of the automated testing system I mentioned at the beginning. How do I start the video? Can we start the video, please? Thank you. So the process begins by uploading a tabular dataset in CSV format into the program. Once uploaded, a preview of the dataset is displayed. By clicking on the column names, users can view the distribution of each variable. After familiarizing ourselves with the dataset, we click Continue, and the system automatically constructs a testing pipeline. The first step is a basic exploratory data analysis. The system identifies potentially unnecessary variables such as index columns and suggests removing them. It then checks for duplicates and missing values. Cells with omitted data can be handled in various ways, for example, by filling them with the mean or a random value. Alternatively, the corresponding rows or columns can be deleted. Next, we select the target variable. And then the program encodes the data. The final step before testing is choosing the algorithms. In this interface, users can add both classical and metric algorithms and specify their hyperparameters. If left unspecified, the system automatically tunes them using grid search during testing. After clicking Next, the testing process begins. Thanks to a bit of video editing magic, I have sped up the process so we can quickly view the final result. Upon completion, the program generates a report in HTML format. This report includes details such as the device hardware, dataset name and size, a history of decisions made during data preparation, and a results table. The table displays the algorithm's hyperparameters, accuracy scores, other performance metrics, and evaluation time. At the bottom, an overall summary highlights which algorithm was the most accurate and which was the fastest. The main idea behind this system is that after some more updates, machine learning specialists will not need to know any programming language to solve simple classification problems. Thank you for your attention.
Thank you. Thank you. Questions? I have question. Why do you need such a specific task to develop your own from scratch algorithm? Yes, if we see that classic approach is okay.
It is like a research. We try to find better ways to solve problems.
Okay. The next question. I see that you use PRIP'2025, yes?
Yes.
Did you try Streamlit for Streamlit library, Streamlit framework for demo development? It's a good solution for data science in general.
I didn't try it.
Try it. Thank you. Thank you. Yes. Mm-hmm. The next report, FPGA implementation of quantionic full connected neural network for image classification from Osipov Alexei.
Yeah. Hello everyone, my name is Alexei and I want to present our work about FPGA implementation of quaternionic neural networks. A few words about quaternions. A quaternion algebra is an add-on over real numbers and complex numbers. The most interest operation in quaternion algebra is multiplication of quaternions, or other words, a Hamilton product. As you can see, every component of input quaternions involves two output quaternions. The quaternions are very useful when we say about multidimensional data and data processing. As example, we can represent data. We can represent colorful images as a matrix of quaternions. Each component of pixels, like RGB values, take place near image part of quaternions, while real part is hardwired to 0. So this quaternion is called pure quaternion, and in this case, coefficients in neural networks works like rotation and scale operator, as shown on the image on the figure number 2. If we say about quaternionic neural network layers, they work the same as real valued layers, so it's easy to implement. A few words about activation functions. The more commonly used the split activation functions that process all components separately, but there is also more complex and quaternionic activation functions exist. We choose a classification tasks over CFR10 dataset. This a structure of our neural networks based on other structure. The most firstly, we use leaky ReLU functions over just ReLU functions, and also we have removed softmax function on the end, so there are 3 output quaternions on the end, and each component of quaternions represents every class of dataset. So there you can see some output of training. First one is a training course on the left side, and on the right is confusion matrix. However, quaternions are not gives very good result. Quaternions and real numbers, real valued neural networks gives the same result for the classification tasks, but more representative results gives the autoencoder task. As you can see, here you can see difference between real numbered structure and quaternionic structure. As you can see the matrix difference and even output results of encoders. So about our works, the main goal is to create IP core for neural networks. We might sorry. First of all, all weights of quaternion neural networks should be stored in the external memory, such as DDR. Second one is that our IP core should be dynamically or static parameterized. So on the slide there is some features that are already implemented. First of all, we have all main layers supported, and we have two-stage pipeline structure of our IP core. On the slide there is a structure of our IP core. There you can see double memory RAM, double buffered RAM block. You can see 2-axis stream interfaces. Also there is a DDR access interface. The blue block is a control unit. The yellow block is the executive unit. Also there is a multiplier and accumulate unit inside executive unit. You can see structure of our design, and our IP block is connected to the processing system core and DDR memory through the standard interfaces like axis stream and axis light interfaces. Some words about conclusion. We already have IP core implemented on FPGA. We also want to learn about about partial reconfiguration feature for our IP core, and we will learn about quaternions and quaternion structure for different tasks, and also quaternionic activation function. That's all for now. Thanks for listening. I welcome any questions.
Please, questions? Thank you. I have several questions. First of all, as I understood, you implement neural network, for example, using Python and deep learning framework, yes?
Yeah.
After that, you use a specific board and FPGA for model deployment.
Here we have used Sync Z7 for our work, and we have IP core that has implemented in this board.
Okay. Did you calculate? Did you calculate inference time for your model? Did you compare this inference time using a specific board with, for example, PC with GPU or CPU? I try to understand the benefits of using FPGA board for a neural network in general.
Okay, I see. This design is the main goal of this design is to implement specific IP core that can be calculate neural networks tasks for the specific task. In the future, it may be works in some core on the processing system, and it might work faster than using CUDA cores or others, but it's very specific task. Have very specific tasks. On the slide you can see the frequency, result frequency. This frequency is based on the first iteration of IP core, so it's not fresh, it's not very fresh, it has only one stage pipeline, and we try to store all data directly on the programmable logic. So the new design is much faster than 66 megahertz.
Okay, thank you. And the next question, I understood that you used convolution architecture for classification, yes,
yeah,
in general. But I saw coder-encoder architecture. Why did you use this architecture? For which task you use it? Please repeat.
This task is the work of my co-workers, Nikolai Petrovsky, and this task shows the more it represents difference between real valued numbers and quaternionic layers.
Thank you.
Thanks.
Thank you very much. Take a seat. The next speech will be online, yes? Encoding and information protection algorithms in digital communication channels. Бекеева Марал, Раздугдеева Гульшат, Разанова Огульбиби. Who will be? Нет. Okay, we will skip this speech, and the next one will be online too. AI assisted static and dynamic analysis for foundation beams with variable quickness on stochastic elastic foundation. This topic from Aslan Tashiliyev and Aman Sahedov Sharia. Who will? Okay. Let's continue offline speech, listening. Okay, and the next topic. Kuzmin Andrei, Kireev Nikita, and Vychuzhanin Mikhail. Yes, yes, and Mikhail will present the topic: determination of movement types based on wrist accelerometer data using machine learning technology.
Good afternoon. My name is Mikhail Vychuzhanin. I'm from Penn State University, Russia. The title of our presentation is the determination of movement types based on wrist accelerometer data using machine learning technology. Mobile information technologies are actively used in many areas of our everyday life. This trend has not bypassed the medical field, including due to the availability of mobile devices such as smartphones, tablets, smart watches. New opportunities have appeared in research and scientific activities, and working with various sources of information has become much easier. Currently, the use of mobile information technologies in the medical field, including the use of smartphones, tablets, smart watches, and our devices. Wireless technologies is rapidly growing area of maintaining and healthy lifestyle. To implement it, software applications are being developed that track a person's motor activity, analyze your sleep cycles. One of the simplest and most common option for tracking human motor activity is the analysis of a 3-axis accelerometer sensor, which is built into almost all modern mobile devices. Accelerometers are actively used to collect the data of human physical activity, which is demanded in the areas such as medicine, sports, fitness, and virtual reality. In medical research, accelerometers provide high measurement accuracy, multifunctionality, and the ability to integrate with other sensors and technologies. This makes them an important tool for diagnosing, monitoring, and rehabilitating patients. However, accurately classify different types of physical activity remains a challenge to a large amount of data required, a variety of movement types, and the influence of external factors. However, using machine learning methods to clarify different types of movement may be an effective solution to this problem. Let's consider a practical issue of registering in mobile application various diagnostic data obtained from the Liget Watch 2020 smartwatch using the built-in BMA for 123 3-axis accelerometer sensor. This model of smart watch is assembled on the basis of EPS 32 microcontroller equipped with Bluetooth Wi-Fi modules. In addition, the platform is open and allows you to program this smart watch to your requirements, create your own used interface, establish direction via Bluetooth Wi-Fi modules with peripheral devices, in our example, to a smartphone. Additionally, it can be noted that the selected mobile platforms has flexible equipment with a hardware and software complex for scientific research, has standard software modules that makes it possible to determine the set of recording devices and the equipment configuration for the next study. The Arduino environment is suitable for flashing this device. Libraries and examples of a watch and located on the GitHub page. Let's configure the Liligate Watch 2020 smartwatch by flashing and version with a built-in Bluetooth model for working with peripheral devices. Picture 1 shows the smartwatch menu for registering and transmitted data from the DMA 423 3-axis accelerometer to connected smartphone. Data collection and recording from the 3-axis accelerometer DMA 423 of the Liligate Watch 2020 smartwatch is carried out via Bluetooth connection using mobile Android application installed on the user's smartphone. Wireless communication via Bluetooth between the watch via accelerometer and the smartphone is pre-registered for your use. The smartwatch is attached to the human wrist. Picture 2 shows the graphical interface of a smartphone. We will preprocess the obtained data from the DMA 423 accelerometer from the Liligate Watch 2020 smartwatch using mathematical linear methods to classify human movement types such activities as running, walking, sitting. The data obtained from the accelerometer are acceleration time series. Categorical cross entropy and CGD optimizer are used in training and evaluating the model as a loss function. The model was trained on experimental data using the backpropagation technique. The model performance was evaluated after training on the validation and test datasets, including the following metrics: recall, F1 measure, accuracy, and confusion metrics. For the final evaluation of the model performance after tuning it is tested on the test dataset. Picture 3 shows the obtained result of the model training. The accuracy change curve of training and testing samples by training epochs. Picture 4 shows the obtained results of model training, the loss function curves on the training and testing samples by trainer epochs. The green and red lines shows smooth values, which allows us to see the trends more clearly without noise. It is clear that the accuracy of the training set gradually increases, reaching a value of about 99%, which indicates good model training. The training loss decreases with each epoch, which confirms successful minimization of error functions. The validation metrics have a smaller amplitude of accumulation due to smoothing, but generally follow the general trend, which indicates the absence of scientific overfitting. The confusion matrix is shown as two versions. Picture 5 shows the absolute values of the numbers of correct and incorrect classification by class. And the picture 6 shows normalized values showing the proportion of correct classification relative to the total number of objects in each class. The matrix shows that the model most accurately recognized the class walking with accuracy of 97%. For running and sitting, there are small errors. Mainly, the model confuses running with sitting and vice versa, which can be explained by simultaneously of some movement parameters. RC receiver operation characteristic for each class demonstrate high sensitivity and specificity of a model. Vary under ROC curve values are close to number 1, including a high ability to a model to separate classes. Precision recall curves show the balance between recall and accuracy by class, which is especially important for evaluating model with unbalanced classes. Picture 9 shows a two-dimensional projection of original data using the principal components analysis PCA, where points of different colors correspond to different activity classes, walking blue, running orange, and sitting green. A good visual separability of the classes confirm that the features extracted from the accelerator data are informative and enough for successful classification. Thank you for your attention.
Thank you, Mikhail. Questions, please? I have questions. Of course, if we speak about limited devices, yes, it is very important to have not only a good accuracy for machine learning model. We need to have a good inference time, suitable size of model. Yes. What about the second and the third parameters for your model? Because you spoke about accuracy, yes? Did you face some problems when you did during deploying your model into mobile device?
Thank you for your question. Now we the very beginning of the journey, the first result, now we receive first result. In future, we plan to extend our research.
Thank you. Thank you. Good luck. Take your seat, please. Thank you. The next report will be from scientific team. Chen, yes, Chen will present this speech combining hierarchical clustering and multi-stage feature selection to identify drug-resistant associated single nucleated polymorphism in Mycobacterium tuberculosis. Please.
Hello everyone. I'm honored to present our research on the combination hierarchical clustering and multi-stage feature selection to identify drug resistance associated single nucleotide polymorphisms in Mycobacterium tuberculosis. My presentation is divided into these sections. Let's start with a brief overview of genome-wide association studies and single nucleotide polymorphism. GWAS is a powerful approach that analyzes the genetic variant to identify association with traits. SNP, the most common type of genetic variation, are single base pair change in DNA sequence. The challenge in GWAS is train the model require a lot of computational power. The figure shows the S&P. In GWAS problem, we start with raw sequencing data from each tuberculosis isolate. This data is typically in FASTQ format. Our first step is to align this read to the reference MTB genome using tool like BWA or VCF2. After alignment and variant calling, we can represent each sample as a sequence SI, where each SIJ is 0 or 1. 1 represents mutation and 0 represents no mutation. For each drug D, we can divide the sample into two classes. Resistance sample denoted as CD plus and sensitive sample denoted as CD minus. This slide shows the workflow. As shown on the left side, prediction starts with the pre-processed VCL files. First, we extract the SNP matrix from these files and use it in the clustering model. Based on the clustering result, we then pass the SNP matrix into matching drug resistant predict model. In the end, we get the predict result for each sample. About clustering model, we use hierarchical clustering on the SNP matrix to assign each sample a predict cluster, and we use the cluster label as the sample's phenotype. Then we use the feature selection and train a random forest model to predict the cluster. For the drug resistant predict model, we use the SNP matrix with the observed phenotype. After feature selection and we train the random forest model to predict drug resistance. About feature selection process have 4 steps. First, we calculate the MDA for each feature and keep only the ones with the positive MDA. Next, we calculate the MIC value for retained features, sort them, and select the top key important features. In the third step, for each important feature, we selected n SNP pairs. Finally, we take all SNPs from these pairs and use back-forward feature elimination to get the final feature subset. We use the data collected from TB Portal program that include genome and drug susceptibility testing information. The number of samples was 4,044. In this study, the mark was set to 5%. This table is the characterization of the data set. For example, for first line drug, for first line drug, lifamycin has 1,474 sensitive samples. This table is the silhouette coefficient analysis for cluster validation. The silhouette coefficient ranges from 0 to 1. A higher value means the number of clusters are better. The optimal number of clusters is 5. With the highest silhouette coefficient. This figure shows the frequency of 13 selected SNPs in the 5 clusters. Each panel represents one SNP. Blue bar shows the frequency of no mutation. Red bar shows the frequency of mutation. The x-axis is the cluster label. With these SNPs, the clustering model achieves an average accuracy of 98% using 5-cross validation. The heat map shows the distribution of normalized accuracy. On the y-axis, you will see different options for the number of important SNPs is k, and the number of SNP pairs is n. The x-axis is the clustering level. Each cell is the normalized accuracy for a specific Kn cluster combination. The best Kn combination is is different for each cluster, which shows that predicting the cluster for each sample is necessary. We compared our results with baseline prediction tool, TB Profiler. For first-line drug, our mask outperformed TB Profiler in accuracy, and for PCA, the predictive result is close. All results are based on 5-cross validation. This table shows the results about second-line drugs. Here are the main findings from our studies. First, the traditional method like to use incremental feature selection and just one feature evaluation matrix, so also that the final model include more features. In addition, some research showed that the same mutation can lead to different resistance response in different lineage. Therefore, we use simple clustering and multi-stage feature selection. Second, our results shows better prediction performance for some drugs. Third, unlike TB Profiler that depend on mutation database, our research doesn't require. Therefore, our approach is easy to apply to predicting antibiotic resistance in other diseases. That's all. Thank you for your attention.
Thank you, Chen. Please, questions? I have questions. Please. clusterization, yes? Because the quality of classification depends on the quality of clusterization.
Let's see.
Did you calculate, did you measure specific metrics for clustering task?
I used how to say it? I used the silhouette coefficient to find the best cluster number, because if you directly give a cluster number, it's not good for next classification. So we used this coefficient to
Thank you for your explanation. Thank you.
Thank you.
The next speech will be from Ильенко Vadim, Neural Network Architecture Search Approach for Telemetry Data Classification.
Good afternoon, dear colleagues. I'd like to present you the report on the topic Neural Network Architecture Search Approach for Telemetry Data Classification. So one of the most important tasks at all stages of the life cycle of a small spacecraft is the analysis of its telemetry information on the functioning of the onboard equipment of the spacecraft in terms of determining its technical condition to ensure its normal and safe operation. A large amount of information received and accumulated in specialized data banks about the onboard equipment of small spacecraft can be effectively used to improve the process of determining the technical condition of a small spacecraft. Due to the fact that data on the functioning of the onboard equipment of a small spacecraft, including telemetry measurements, are heterogeneous, irregular, and multidimensional data, it is relevant to research, develop, and apply models that allow analyzing such data with the possibility of extracting useful information from them and then constructing classification and predictive models in order to determine the technical condition of a small spacecraft, in order to make correct management and operational decisions during the operation of a small spacecraft. The method of machine learning, artificial intelligence, and mathematical So here you can see the neural architecture search pipeline. Neural architecture search is a subset of automated machine learning, and it is the process of automating architecture design when data is received as the input and the task to be solved is formulated. And the output is an architecture that gives the best result. Here are the main search spaces used in neural architecture search. Among them, hierarchical, chain structured, macro or layer-wise, and micro or cell-based. Main elements of this neural architecture search are operation or primitive. It denotes the atomic unit of the search space. For nearly all popular search spaces, this is a triplet of a fixed activation operation and fixed normalization. Layers is often used in chain structured or macro search spaces to denote the same thing as an operation or primitive. However, it sometimes refers to well-known combinations of operations such as the inverted bottleneck residual. The next block or model is sometimes used to denote a sequential stack of layers following the notation used in most chain-structured and macro-search spaces. A cell is based to denote a directed acyclic graph or DAG of operations in cell-based search spaces. The maximum number of operations in a cell is often fixed. Motif is used to denote a subpattern formed from multiple operations. So there is a description of experiments. In the figure below, you can see a telemetry file fragment. The main idea is binary and multi-class classification. 3 sets of telemetry data from the Belarusian spacecraft star sensor for the period of time from 2015 to 2021 were used to build machine learning models. The telemetry of the Belarusian spacecraft star sensor contains sensors that determine the following parameters: solar coordinates, current on the star sensor, quaternion values, the temperature of the signal processing process, and the temperature of the CCD sensor which takes pictures. Also, each object in the table has 2 labels for binary classification. It has a label class and 5 states for multi-class classification, class 1 label. But multi-class classification is only available in the most biggest telemetry file. 2 other small data sets doesn't have this last column. So there are the key elements of neural architecture search approach, which was used to conduct the experiments. So the transformer architecture is used as a basis for conducting experiments, which is well suited for processing sequential data such as telemetry information. The basic elements of the architecture being developed are fully connected layers or dense layers and the multiple attention mechanism. When designing the architecture, the multiple attention mechanism was complemented by layers of addition and normalization. In this case, the addition layer performs an operation of piecewise addition of the input and output values. A NAS neural architecture search approach was performed for each of the 3 experimental data sets. And here you can see an example of found neural network architecture for multi-class classification using sort data set. As I have mentioned, it has 1 extra label, class 1. So, and on the last layer you can see 5 neurons with softmax activation function. So the following slides will show the result of the experiments. So this is binary classification problem solution. Results on the first data set. Here we achieved around 0.97 precision. So here is the binary classification report for the second data set. Also rather good results, as you can see. And the last one, binary classification problem report on the third dataset. So this is the last binary classification report. And next, it is a multi-class classification report. There you can see the maximum achieved value of precision, which is around 0.85. So in the conclusion, I'd like to say that the proposed methodology implemented using deep learning framework employs transformer-based models and combines random search and reinforcement learning to navigate hierarchical search space efficiently. Development of a hybrid search strategy outperforms manual architecture design. Creation of task-specific architectures demonstrates approximately from 7 to 9% accuracy improvements. So this diapason is related to the task and the data set. So thanks for your attention.
Okay. Yeah, thank you. This applause for you.
Please, questions? No questions. Thank you, Betsy. Oh, what?
So in short, so once you classified this data, what next? I mean, what they propose, the main goal of the classification, and what kind of decision making?
The main goal of this research is to improve previously used ensemble methods results. So as you can see, there are rather good improvements to almost 10% in accuracy. And these results will be used in program with Russian colleagues concerning the cosmos, the cosmic spacecraft monitoring task.
Yeah.
To monitor what? I mean, the statement of the aircraft, of spacecraft, like this, yes?
The state of the onboard equipment of the spacecraft.
Yeah, so it means that if there is some kind of non very known anomaly, so this classification will help to make a decision making to prevent some kind of well, what? Could you explain a little bit clearly?
We can monitor the state of the spacecraft, and in further our research, we will use it for decision making, of course. Now it is only a part of future research. We want to, for example, to switch off some equipment if it will break in time.
Okay. Thank you, Vadim. And the last speech will be from Angelina Vashevich. Depends of preventing attacks in the task of classifying medical images. Angelina, please.
My work is named as Defenses for Preventing Attacks in the Task of Classifying Medical Images. The purpose of this work analyzing existing attacks attacks and study the problems of detecting and creating dependence against them on neural networks for medical image classification. It's really important because neural networks are very sensitive for the quality of input data. The objective of this work is developing defenses for protecting neural networks against attack in the task of medical image classification. So, in this work, I researched efficiency of existing defense adversarial training and proposed defenses blue reconstruction, denoising autoencoder, denoising variational autoencoder, for operating such attacks like fast sign gradient method and Karlini-Wagner. Attack is a set of actions that adding noise to an image which invisible to human eyes, but after adding this noise, neural networks work incorrectly. In other words, after adding noise occurs multiplication, and image which made with these attacks named adversarial images. Defense is a set of actions that make a neural network behave on adversarial image as if it were on unadversarial images, real images. For experiments, we chose two datasets, first with computer tomography slices of heart, shoulders, and livers, and second one, there is a histology dataset with three classes: norm, epithelial, and tumor. Custom neural network and pre-trained efficient net B2 were used for classification tasks, and there are Karlini-Wagner and fast sign gradient method attacks were reproduced. The main aim of fast sign gradient method attack is adding noise to each pixel of the image using formula 2 for making an adversarial image. When the aim of Karlini-Wagner attack is adding noise to a minimal number of pixels in image. So the main difference between these attacks that fast sign gradient method modifying each pixel of image, when Karlini-Wagner modifying small number of pixels. Based on the results from this table, we can conclude that the Karlini-Wagner attack is stronger than fast sign gradient method because accuracy after attack is 0%. And we want to prevent these attacks. So one of defense that can prevent fast sign gradient method and Karlini-Wagner attacks is adversarial training. Adversarial training defense include additional training the model on adversarial images. This defense has good results, but it has a serious problem. We must know the type of attack and adversarial images before training. Blue reconstruction defense include adding median filter on the image The motivation is that the median filter will be able to reduce the impact of adversarial noise. The results show that it doesn't worsen the original classification accuracy, but can't be used as a standalone defense. The remaining defenses are aimed at reducing the noise from adversarial image to real image using encoder-decoder architectures. Difference between denoising autoencoder and denoising variational autoencoder defenses only in latent spaces. So in this slide we can see latent space from autoencoder and this latent space from variational autoencoder. This slide shows the results of using denoising autoencoder defense to prevent fast sign gradient method and Carlini-Wagner attacks. This slide shows similar results for denoising variational autoencoder defenses. And if we accumulate results of these two defenses, it was found that denoising variational autoencoder works better in histology task, but denoising autoencoder works better in computer tomography task. But it's really important that all results are good enough for independence defenses. So the choice of defense depends on task being solved. So I can make some conclusions. The first one, Carlini-Wagner attack is more effective than fast sign gradient method. The second one, defenses noise autoencoder, denoising variational autoencoder can be used as independent defenses against the Carlini-Wagner and fast sign gradient method for task of classifying medical images. And the third one, blue reconstruction can be used as a part of composite defense. Thank you for your attention.
Thank you, Angelina. Please, questions? I have a question. You mentioned two architectures of neural network, custom and efficient net, yes? Could you give us more details about custom architecture?
Custom network is just a simple convolution-based network for classification.
Is there any big difference between efficient net and your custom model? Or you used it only for experiments?
Yes, there is difference between them because first one, that efficient net V2 is larger and is more effective because it's used in mobile phones and inference is faster.
Okay, thank you. Please.
Thank you for this interesting topic. I'm just interested, is it important, is it actual for medical images? I thought that neural networks attacks is more actual for security systems or something else, but does someone need to attack medical network?
Yes, because we can see in other side, for example, you have some corruptions in that data and neural networks will have different results if you give them just normal data and some corrupted data, and this corruption can be like adversarial noise.
It's essential for medical data.
No. It's can be and for medical sphere and for different sphere. The main aim of this algorithm to make backward by gradient and to make adversarial image. So the sphere is not important, but we say about medical sphere because we can use in it.
Okay, we can send data. We can send data.
Yes.
Thank you very much.
You're welcome.
Thank you, Angelina. Our section is finished. Yes.
Yeah.
Alexei, please.
Thank you, Madam Chairman. Madam Chairman, yes. And so we're closing scientific program of the conference. We'll have now short break for 20 minutes, and at 4 p.m. Turn to the final part of the conference, celebration of Lightning Talks winners, and of course closing. And microphone will also be open and open floor. Then after the closing session, you also may chat about your thoughts about what actually was right, was wrong. So the final session will start at 4 p.m. Thank you.
Machine and deep learning, computer vision and signal processing, artificial intelligence and neural networks, cloud computing technologies, and more. Pattern recognition and information processing, embedding the future. Once upon a long ago, a man looked up to the sky and saw the stars. His heart was struck by a spark of passion for knowledge. He invented the wheel, tamed the power of wind, steam, electricity, and the atom. He learned that knowledge itself is the ultimate prize. And now, here, in a land where the very air is thick with history, where the echoes of the past meet the dawn of the future, where vision is molded into substance, where like-minded people catch trends, where ideas ignite passion. Let the celebration of science begin now. Pattern recognition and information processing. Embedding the future.
Ladies and gentlemen, I hope that actually, so these 3 days will already embed some future. And now we're coming to the very last session, closing session, which will be included, which will include actually ceremony for celebration of winners of Lightning Books. But first of all, I would like to say that I would like to thank you, all of you who are here in this hall. Not all of the conference speakers, but still you're alive, and I'm very happy. So let applause to all of us. These 3 days we had more than 80 talks, session talks, lightning talks, flash talks. We had speakers from 9 countries. So yes, Russia, of course, Belarus, China, Turkmenistan, Georgia, Belgium, Canada. So and now, so actually I will not engage too much time, because probably you're expecting for who is the winner of the Lightning Talk session. But first of all, I would like to invite to this head of the evaluation committee, vice chair of the conference, Professor Academician Sergei Vlameyko. So please. Yes. And a member of the evaluation committee, one of the 4 members of the evaluation committee, Professor Marina Lukashevich. Please. Yeah. So they will present the gift and of course diplomas. And now, as for Lightning Talks, I would like to invite to the stand to get the diploma and the gift from our evaluation committee, Helena Kimpitskaya. So this certificate is proudly presented to Elena for delivering the best Lightning Talk entitled Segmentation-Based Attention Mask for Enhanced Fundus Image Diagnosis. So please. So remember that actually our Lightning Talk is held in honor of John McCarthy's birthday, because on 4th of September in 1927 was birthday of John McCarthy, one of the founders of artificial intelligence, and in next 2 years we'll celebrate 100 years. Yes. Well, the next speaker who will be certified with recognition, Artyom Khalyan, for delivering the best Lightning Talk entitled Methods for Reconstructing Part Training Images from Pre-Trained Neural Networks. Please, come on the stage. Okay. No, okay, so we will, yeah, okay, we will give the gift later. Yes. Okay, and by the way, the gift which are given for the best lightning talks are from our general partner, WebTech. So WebTech is a fintech company doing science and doing applied research and development in the field of not only fintech but also artificial intelligence. And the third, last but not least, and not third but also the best, lightning talk entitled "Machine Learning Approach for in Searching Novel Human Automatized Inhibitors." Marina Shaladanova. Okay. So these are three best lightning talks, but we have outstanding lightning talk. So this certificate is proudly presented to Johan Sie. I'm not sure he's online, but still. So the online lightning talk, delivering the outstanding lightning talk entitled TCS, an algorithm for focusing on the segmentation of tree crowns and trunk in forest point clouds. As I remember, he's from Nanjing, I think. So I will give it also to Evaluation Committee Chairman, and we will send this present, yes, to... Now please, all lightning talk speakers who are in this call, please come to the stage and we will have a general quota. Lightning winners of lightning talk. Yes, again. Again, please come on the stage. Yes, just to make up with... Yeah, like this. So again, applause and a photo. We have... Okay, I think the photograph is here. Okay, let's applaud. Thank you. So, now we're coming to the... Thank you, Chairman. Thank you. And now we're coming to the closing session, and I will give the stage to the head of the conference, Chairman, Professor Alexander Tuzikov. Please.
Okay. Dear colleagues, I will take this one. We had 3 days of very intensive work, many talks, many presentations, and it was our idea from the beginning. It was just to have only one PRIP conference, so to be able to listen to everybody. But because we accepted too much presentations, so we decided not to have long talks, but middle, short, and very short talks. And in fact, it's very good. These lighting talks, I suppose, it's a good idea because these presentations were very concentrated and much more easier to understand, because usually people were preparing much for their presentation, and in a condensed mode they presented their results. Even it was easier to understand because it was necessary to spend more time to prepare and then present the results. So it was, from my point, a good idea. So the proceedings of the conference are also available, but there might be some mistakes. So if you will find some mistakes in the proceedings, please address to the Alexei Belotserkovsky, and he is able to introduce these mistakes and make corrections in the final proceedings, which will be at the conference website. Yes, and we also plan to then select several presentations and negotiate with the authors and with the publishers concerning the publications of extended versions of their presentations. Naturally, it will be necessary to pass the procedure of reviewing procedure in the journals, but it will be something like special issues or of part dedicated to this conference, PRIP 2025. So I would like now to close this conference, but I would like to say that it's usually it's for people which are living at the place and organizers of the conference. They are not able to participate at all the events at the conference, and it's advantage to come to the conference from other places. But for conference organizers, it's a very big job to prepare a conference at a good level. And I would like to thank from you and from also us people who contributed very much to this conference. First of all, I would like to thank all people who contributed by their presentation, their reports. It's all of you. But also I would like to thank very much good words to Chairman of the Organizing Committee, Dr. Alexei Belotserkovsky. Alexei, please. For this great job he done organizing this conference, spending a lot of days and also nights for preparation of all these conference materials and website and everything organizing related to this conference, and also people working jointly with him and just making all this infrastructure for conference available. I also would like to thank you very much. Thank you very much, colleagues. Thanks a lot. And I would like to say thank you also from your name, the chairman of the International Program Committee, Dr. Alexander Niedzvich, and Dr. Marina Lukashevich, who organized this verification and the reviewing process of all the reports submitted to the conference. And I also would like to express my hope that you enjoyed this conference, and I invite you to participate in the next conferences, 2026, which are on the regular basis organized in Minsk and in several places, but I hope that we will also organize the next one. Okay, thank you very much to everybody.
Yes, I think that.
Or you will present, okay.
Again, so with a very kind and laugh, I would like also to present again, to step on the stage, academician Sergei Blameyko, who is the vice chairman of the conference and the founder of the conference Pattern Recognition Information Processing. Thank you.
Well, I will not speak much because Alexander said everything. It's really a big job, of course, for many people, but Alexei he did a great job, really. And this is really, I would say even that the first time we had a conference, let's say, outside of institute and university, in such a nice building, and it's organized very well. So again, I repeat from all of us, thanks to Alexei for this great job. And of course, we are happy to have a good scientific these 3 days, and as Alexander said, see you next conference, 18, 19, 20, and so on and so forth, because, you know, this topic is very important. I mean, all this pattern recognition, computer vision, artificial intelligence, deep learning, and so on and so forth. It has a great attention from companies, from universities, from all those things. So, all the best for you, and see you next PRIP. Thank you.
Yeah. Well, now if you have any idea to share, we'll have an open floor. So please come on the stage and say something so it's available. If not, well, what actually I also would like to thank all of you, first of all, because without you, without so many people, so actually we submitted around 200 papers, but so international committee had to select at least half, and even with the half of these 200 papers, very condensed 3 days, and you realized how difficult to organize it in one track, but to organize different tracks, several tracks, is also not very good because all of topics are quite similar, not very close to each other. That's why probably to be in the one hole it's better than going there and there and trying to choose what kind of track should you listen. That's why first time, I mean offline, first time we select the choice when we have just one track. In 2021 it was the first time when we had a fully online conference, and so that time it was very successful. That's why probably it was a very motivative thing for me to organize this, to be organizer of this in this time in the hybrid mode. Well, of course, if you're online, it was possible to have more countries. That time it was 18 countries, but now still 9 countries is also okay. And I'm very happy that we have very widespread geography, and here we have people from west and east and very east part of the world. And of course it wasn't possible without technicians, and I hope that you realized that everything what was done, what was concerned about reports, what was concerned about online, is done by just one person, and he is absent currently, no? Actually, I wanted to thank a guy by the name Yuri, and of course staff of my friends who are cameramen. Yes, so Armen and Alexander. So hi. Okay. Yes, because even if you think that was something wrong with sound and picture, forget about this, because all in high quality will be online in VK and YouTube, so you may realize that after several weeks you may just notice something new if you remind reports by yourself. So again, so let's make an applause to Yuri. It's for you. Yes. He did everything like a robot and spent a lot of hours with these things. Well, if we have no left, it means that it's time to have some champagne outside. I'm not sure if you want. I'm not sure. It's actually so. As for schedule, champagne will be in 20 minutes. But probably if we ask hostess, probably they will organize champagne right at the moment. And I hope that you arrived here not by car, because it's a very good time to celebrate the end of the conference. Thank you all. Thank you. So, another nice idea, just come here, all of you, the bravest men and women, ladies and gentlemen, and to make, well, general photo, please.
Teenagers are building businesses with AI.
And now goodbye coffee and champagne.
Machine and deep learning, computer vision and signal processing, artificial intelligence and neural networks, cloud computing technologies, and more. Pattern recognition and information processing, embedding the future.